some my impression connected with a narrow topic of photocatalysis is focused on water splitting. Since I'm a physicist, not chemist, not working in, for example, in chemistry, I focus on physical foundation of such phenomena, especially on as similar like in previous lecture on adjusting materials properties to our demand, to our requirements, because it is important work. But from my point of view, for green energy, possibility divide or separate hydrogen and oxygen is very important from not only economic point of view, but also from climate and next dozen years in near future. For many years, people not strongly influenced in your climate in Earth, but now, when you see how much cars, how much pollution from industry destroying our Earth, it is important because people thought that, for example, nuclear energy is also safe and green because we not generate CO2. It is not good, because you should remember how working a system which utilizing nuclear energy. It is producing heat, and only a small part of heat is exchanged or transformed in mechanical energy, and such mechanical energy also in the next step is transforming into electricity. Second problem is with transporting energy, because it's a different evaluation. 10–15% of energy exchanging into heat during transportation to end users. It is also a great problem because it's difficult solve. Because, for example, anybody like when a nuclear station will be near his house. It is not good, but what is the great advantages of splitting water? And for example, like in India and some countries when it's a strong sun radiation, it is some strange situation, because for lifting we need energy when energy is forbidden because solar cell is not working because it's night. Second problem, it is very, very important in Europe. European community move huge money for supporting solar cells farm. And people grow big farm producing huge energy, but it's a problem with such energy. Because in day is very often difficult to consuming, but also is a problem for transporting or dispatch to another place. It is a problem with a flow inside electrical network. But what is it? When we have opportunity utilizing some solar energy which is not consuming into hydrogen, we can solve some problems because we can use, for example, such energy we exchange for fuel to cars. And what is the pollution from burning hydrogen? It's water. It is any problem. And from such point of view, a topic is very important, but problem is also in details, because idea is very simple. As you well know, it is a special requirement for electrode material, and we can do it. But it is a problem with resistance, with efficiency, with some technical details. Because, as I told, idea is very simple, but application sometimes is difficult. I will divide my talk for a few milestones. It is at first I talked about a principle and method of water splitting, and next I focus my interest on improving efficiency of such process, because all processes which we will discuss today and we discussed previously is not high efficient processes, but we not be confused, because sun energy is free, and if we exchange some solar energy into electricity or into gases which we can use in future for exchange for mechanical energy, is very important. And here I would like to focus on 4 topics, and band gap engineering, doping, semiconductor alloys, and nanostructure. From my point of view, when I focused on such topics, it is maybe joining one, because, and maybe last topic, it is nanostructure, is maybe quite different, because as Professor Azem explained on his talk, except opportunity to managing band gap of materials by utilizing a small element of bulk materials, which we know nanomaterials. It is maybe ultra-thin films. Recently, maybe 20 years or more, almost 30, start a great interest in 2D materials. I show you a paper which is very simple from a fundamental point of view, because it's a paper regarding quantum chemistry calculation of a simple structure. But it was more than 2,000 citations, because it is connected with 2D materials for photocatalysis application. It is also some remarks from my long career regarding citation, number of papers, etc. You know that a person like Einstein was being refused from university very fastly because he not published sufficient number of papers every year. Yes, and also when you're working in very narrow branch, not popular but fundamental, people not citate you because people interesting or working in the same subject is few. It was also my impression after collaboration with my colleague from India, not far away, from Vijayawada, when I start collaborate with him with luminescence of glasses. It was enormous increasing of citation, but Professor Variach told me in India we have more than 2,000 persons which are members of Indian Luminescence Society. But for example, when you're working in black holes or another topics, it is a great difference. And also, you don't afraid when you put application for a PhD or postdoc position, because sometimes, many times, or mostly, people looking for a person which able to do something. It is expert, for example, for thin films grow, crystal grow, sophistical measurements. It is also very important in doing science and in all your career. But we back to and photocatalysis may be used not only for water splitting, but also for cleaning water. I told most generally, cleaning water, because we have some pollution in water, especially it is agricultural industry origin, because I thought of agriculture, because when you cultivate in small area, you not use special chemicals, but such chemicals also, like today, after strong rain, move to source of drinking water. And from such a point of view, it is a very interesting topic, and I think is crucial because we can use a free energy, because energy up to now in our European community is not connected with a task. For example, when we buy gasoline, it is 60% of price is task. But I am afraid when start put some task for electricity from sun. Okay, and what is a picture? It is, you can buy as such, it is a probably Nissan or Hyundai, I don't know what is a Trada make. It is a car for liquid, for hydrogen, not liquid, because hydrogen is difficult to be liquid, but hydrogen. And for example, in Poland we have two fuel stations only. It is a problem for future. How will be solved? But I think that from economic point of view, when will be problem with conventional energy, such car will be popular. But here is a problem with storage hydrogen. You can also thinking about such topic, because most of you working in nanomaterials, on porous materials, and it is a possible topic for application for hydrogen storage, because as you see, we have a few problems to solve for application. You know that in opposite to gasoline even or diesel, we have a problem with very dangerous fuel, because they need anything to be exchanged from nice eco-friendly fuel into bomb. And such a problem of utilizing light to splitting water is not young. We have a very long tradition for discussion about such possibilities. But from such point of view, problem from chemical point of view is quite simple. We should add to molecule of water some energy. It is a Gibbs energy, which is not so big. It is equivalent 1.23 electronvolts to utilizing light, divide hydrogen, water for hydrogen and oxygen. And what is requirements to such photoelectrode? Is active element which help nature to divide water. Special band gap, but it is from one point of view. Low electrical resistance. It's a problem because a semiconductor not usually have a small electrical resistance. Most important, good corrosion resistance. It is a great problem which arises in many application of materials. We have very good materials for particular application, but it's a problem that may be very fast destroyed. It is also like you maybe part of you working in biomaterials for medical application, when we have excellent materials, excellent properties, but after abandoned to human body, which we tested utilizing, for example, body simulated fluids, such materials very often at first interact with such environment and also may be destroyed. It is a little bit problem, except fundamental problems. High photon conversion efficiency. It is necessary to generate a pair electron hole. What is it? Fast charge transfer with electrolyte. It is also important. And last, durability. And next will be question, because mostly in science we not discuss, but when we make commercialization of our idea, a great problem arises with cost of manufacture. It is also crucial because we not need small devices, but we need big or great devices for industry processes. It is also great problem for such producing element. And also, should we remember about future? It is low cost and easy for maintenance, because some equipment may be not so expensive, but maintenance it will be expensive. It is a problem because such maintenance should be, for example, performed frequent exchange, and also when we produce such devices, we also should remember about it. And for example, I told from different point of view, when you should exchange element for $200 expensive in Audi car, you should remove engine. Because engineering forget about lower expenses of maintenance, and it is necessary to 15 times more pay for simple work. And also, I would like show information about a place when you can apply for postdoc, for PhD. It is a leading institution in our country. It is Institute of Physics, Polish Academy of Science, and my colleague and collaborator, Professor Suchocki, for a long time working in water splitting. He is also expert of luminescence properties. He working in chalcogenide and halide materials, perovskite, double perovskite for different application. And from such point of view, it is a good place for continue your scientific career on initial stage. It is very good. They have a very good laboratory in which grow single crystals, and for different applications. Mostly they grow crystals for optoelectronic application, but when they understand that crystals for luminescence properties may be also useful for application in water splitting, they start working in such topics. And they grow very good photoelectrode based on zinc oxide, and after some experimental tests, because they perform several tests for water splitting, they try to modify such materials. And they perform standard measurements, because we can, utilizing our standard laboratory equipment, to describe properties of materials which possess multi-purposal application. And for example, when you see as grown zinc oxide possess absorption region up to 475 nanometers. But doping enhancing such area, but it is from luminescence point of view, it is very simple and natural process. As I will be very often recall you information how you can, utilizing your own skills, own possibilities, to application and different, to working in different but very similar from technical point of view problem. And it was very simple, but strongly increase efficiency of materials, because as you remember from yesterday lecture, that in such visible spectral range and in UV, energy of sun is most important. But it was some little bit problem with such electrodes, because erosion processes arise. And good material, very simple, well-established technology of preparation, but some problems with durability. Because as you see here, it is after 10 hours of illumination. 10 hours is not so big time when we need equipment for such measurements. And now we can discuss about two possible way of water splitting. And one is a traditional configuration, when we have a solid electrodes, and second, when we have nanoparticles which absorbing sun radiation may be divide or splitting water utilizing a free step. because such three steps are as follows. After interaction sunlight with electrode is a generation of electron-hole pair after absorption. It is a typical process. Next is a charge separation and migration to the catalyst surface. It is also a problem when such preparate electrode material should have such opportunity to migration pair hole electron to surface of active media electrode. And next is reduction water by electrons and generate hydrogen on a surface of catalyst. It is very interesting and simple process. And from physical point of view, is here not exist any problem. It is very simple, well known from first look processes. And is important how fulfill such requirements which we discussed earlier regarding efficiency of process, durability of materials, and also with expenses, cost of preparation and maintenance. And what is this important question and important problem in such? It is right here. To achieve maximal efficiency, we should have not only well-described band gap, but also a position of band gap. And also, as we discussed earlier, should absorbing most of sun energy. It is important from spectral point of view. And here is some groups of materials which are responsible for possible application. As you should remember, but I give you such presentation and also with a list of link to review and special topics manuscript where such problems are explained in detail. We have except yesterday and Monday discussion, we have one group, a so-called nitrides, which is when I was in your age, it was also important utilizing nitrides for generation laser beam in ultraviolet. It was a so-called blue laser. And here we have a big spectrum, and people which working in oxide materials, which working in chalcogenide materials, Also, maybe should a concurrence of nitrides. And also is important to adjust band gap and position band gap to requirements water splitting. And next, I will be present some methods what is solved problem of not only band gap but also adjusting position band gap. And third problem is connected with efficiency of such process. And we have some way. Ordinary band engineering. We discuss about many methods in tutorial. I explain also another method for band gap tuning using so-called intermolecular pressure. But we can do it like we discussed yesterday. We can perform, for example, investigation regarding influence of materials composition. It is one of problem I show you, taking account chalcogenide materials, very useful for tuning band gap. Also, we can using another phenomena is a so-called doping, but it is a doping, I think, here for generating so-called acceptor and donor levels, because depending of valency of oxidation level of doped ion, we have opportunity to generate inside band gap additional levels which give us opportunity to adjusting band gap. And next, maybe here is in left cation doping, and here anion doping semiconductor, and we have adjusting band gap for our needs. Next, we can do it so-called solid solution. We discussed yesterday in detail about it. We can also have opportunity to make a process of generating pair Hall electron using a two-step process in annealing or making alloys of two semiconductor. We also have a next opportunity. It is connected with a special construction. We can put some active elements on surface of semiconductor, also to adjusting band gap and improving efficiency of generation pair electron hole. But during my previous lecture, I told that we many times should or have opportunity to predict some materials properties. Utilizing a modeling of materials, we can have opportunity adopt some software to perform a calculation. It is well recognized method for performing calculation, and now if you like publish paper in good journal, accept good measurements, it's necessary to include a part connected with explain observed phenomena in microscopic level. And quantum chemistry calculation are a very useful tool for such. But now we have many programs. Some of them is free for science. Some is very cheap for science. Some is quite expensive. But when compare expenses in commercial application, for example, for drug companies or pharmaceutical companies, it is price is very low. And what is it? And some time ago was published article. Authors perform some quantum chemistry calculation regarding describing properties, electronic properties of 2D materials. Here it is a cation, molybdenum and vanadium, and here in right side 3 brothers, sulfur, selene and tellurium. And it was surprised for them that such materials may be very useful for application to water splitting, though exceptional properties. Because you know that graphene is a perfect two-dimension material. Double layers of such material not have same properties. It's quite different. But authors try to performing a quantum chemistry calculation for different structure. 1 layer, 2 layer, 3, 4, 5, 6. And compare electronic properties of such heterostructure. Because from a practical point of view, it is very difficult to deposit 1 layer of matter. It is difficult, and the discovery of graphene confirm it. When we deposit layer, 1 layer crystals, it is necessary to preparing a perfect substrate. And also method of deposition 1 layer is not so much, but as such which will be useful are very expensive. But we can go to interesting results because it is important how we can modify materials. In the right side we have energy and top of valence band and bottom of conducting band for 1 layer, 2 layer, 3, 4, 5 layers. As such, publication is also open access, And it was a surprise that how changing a band gap of such two or almost to the structure, because band gap of molybdenum sulfate change from 0.9 up to 1.6, when I well remember. But it is very interesting results, but we can expect, because we go from bulk material to nanoscience, to nano. And it was improving or put some properties of such materials do deposition thin films, all heterostructure, because when we have one layer, we talk about 2D material. When we have a few layers, we speak about heterostructure. But such properties is very amazing. It is also very important information how band gap may be modified, taking account only one parameter like thin film thickness. And it started a huge number of theoretical investigation. As I told, such paper published in no so prestigious journal have almost 2,000 citations. And it was era, I think 1 or 2 years, when 50% our manuscript submitted to optical materials were connected with theoretical calculation of heterostructures 2D, but such diselenite material. Yes. Or the chalcogenide, because it is also utilizing not only sulfur, which was first most important, but also tellurium and selenium. Such a free chalcogenide material, though different behavior, as I recall, I yesterday told, because the sulfur is fully dielectric, selenium is more metallic, but semi-metallic is tellurium. It is, and about such materials is not enough story for today, because in next lecture I also will discuss or take account of such materials. And such information, which was noticed by people working in photocatalysis, start a new era with preparing composite materials, because such two-layer structure were combined with quantum dots, with nanoparticles, and also more complicated structure to achieve better desired properties for water splitting. And now also a few examples how we can utilizing material engineering to improve efficiency of catalysis. Here is an example of interesting application or interesting proposal, because it is most of proposal for solving process searching efficient photocatalyst materials. It is a multifold water splitting, when interaction of pair hole and electron have a two-step process. And also is next application. It is so-called heterojunction, when is nanoparticles connected with quasi 2D materials for improving properties connected with efficient photocatalysis. It's a few opportunities. Also, is important so-called carbon nitride. It is a material which metal-free. It is environmental safe. It is a very good material. Such crystal possess many polymorphic behavior. But it is also very easy to modify such materials by doping. It is important because such fully non-metallic materials, it is sometimes a great problem, and you probably not participate in a hot topic few 20 years ago, maybe more, when was discovered a special crystal structure of carbon. It is, for example, fullerenes. Fullerenes possess some interesting properties, but doped fullerenes, for example, possess superconductivity properties, and also some catalytic properties with nanorods, etc. It is interesting because here is example, it is information how doping may be improving absorption efficiency for such doped materials. It is also quasi two-dimension material. And here is also example of a special kind composite, when we have a sheet of carbon nitrides with famous material for electrode. It is titanium oxide. As such heterostructure possess a very good photocatalytic properties, and here you are able to see how enhancing, how grow efficiency for water splitting application. It is maybe 10 times. It is amazing when we have two materials, and after make composite materials, we significantly improve interested us decided property. And also next example of solution composition for battery for photocatalysis, when here was application of also wolframium oxide and carbon nitrides, and such a two-step process is under consideration. It is tested, but it will be also promising for future application. Next, we have so-called MIOIFI. It is metal organic frameworks. It is also is interesting direction for searching better materials for water splitting, because what is the importance for porous materials? It has like nanomaterials have a great active surface. Yes, because when we have some nanorods, we have some pores, it is surface of interaction with water significantly enhanced. And it is you're able to see how methods, how knowledge, how idea moving from one application to second, because yesterday when we discussed about improving solar cells materials, one of direction very promising is materials which organico metallic structure exist and are very sometimes very cheap, but it is also interesting from future when we should after application, for example, start the process utilization. When I sometimes driving and see some hectares of solar cells, silica solar cells, I thinking how will be expensive expensive a process, for example, utilization after 10-15 years. You know, it is maybe great problem. When you probably you not remember era when was monitors with bubble utilizing X-ray as source of excitation. It was a situation that full process for example, for destroying such equipment, for utilization equipment, but not like people talk that we're melting and removing anyway. It was expenses over cost of production. It was and with silica maybe also a problem. And also is some proposal for solving process of improving or finding efficient photocatalyzer electrode is here is information regarding efficiency of a particular solution. And we see how different is efficiency of some materials, but here is not informant regarding durability of such, because when we buy shoes for 100 rupees and we use one day, it is sometimes difficult to tell it is expensive or cheap. Because when we buy for 400 and we work in 1 month, it is cheaper. But from first as expenses is higher. It is also important, but some of proposed solution give promising information for future, but is still working, especially more sophisticated structure. And here is also information about very old and simple organic elements for water splitting, and we may be told about so-called titanium-based photocatalytic electrode, tantalum niobate-based photocatalysis, and metal nitrides and oxynitrides. It is also interesting that managing chemical composition, or as you see here, preparing more complicated composition, we can improve properties. But in next talk, I also will focus it on such topic connected with so-called high entropy materials, because enhancing of configuration entropy sometimes is a good direction for improving properties of such devices. And here is a comparison of efficiency, different attempts for water splitting, and also is a typical methodology, because we have a core material and changing one of ingredient, one element of composition. It is a typical way for application, for searching new materials, but in such we can find optimum chemical composition. And also, except very expensive and consuming money and time measurement and synthesis process, because you know that not each attempt will be successful. Sometimes we must change many parameters. It's like, for example, like in crystal grow, when we put very expensive ingredients, but a temperature or some another parameters like a speed of moving particular elements not give good results, and we lost expensive materials but here. But do a very sophisticated software for calculation bands gap, because for when we take account for calculation inorganic materials, we use another tools when we try to calculate properties of big molecules. And here is also a proposal application of carbon nitrides connected with nanoparticles of titanium oxide for water splitting. It is also possible we can, for example, utilizing such we have some information about or road of our work, experimental work, and it's probably interesting solution, but I hope many people, maybe in India or China, apply such prediction to obtain a good equipment for water catalysis. And I also try to believe that prediction of theory fulfill, because I have some topological materials and try to confirm or check if such materials possess such properties. It is very expensive and consuming much time. It is sometimes necessary to put a risk. Here is my opinion about future of water splitting, because after check or after read some literature, some discussion with many people is agree as such a conclusion that such process is not so efficient. But from a way, when we should lose energy, we can apply them for application like preducing hydrogen and oxygen. And here is some topics which should be solved or is necessary to open for such question, to have opportunity discuss or improve efficiency of water splitting process. And I hope it will be some break of situation, and maybe some theoreticians which was involved in process to understand from microscopical point of view, to understand such idea, and maybe better predicting materials properties, give us in future significant improving such low efficiency of water splitting utilizing free energy. But thank you for your attention here, and I hope we have a small break now and start next lecture. It will be focused on topic connected with another phenomena connected. It's possible quite easy predict properties of materials, and I show like this paper is constructed. And start is information about importance of such topic of investigation, and next is a method. It is VINA ability of simulating package. It is one of well-known software for predicting structure and properties of solid materials. It is very good and not so expensive, because at universities obtain a discount for site license. It is equivalent a few $100, and all students and staff may perform a calculation utilizing such software. But what is it interesting? That for example, they connect many useful and interesting materials parameters. It is a huge number, and mostly it agree with real materials, and it is maybe when it's some difference, but mostly in science we need to know a tendency. When, for example, when we add such element, for example, band gap decreasing, but sound velocity increasing, etc., we should know to predict materials properties. And also I presented such a picture. It is information. Also is charge density is calculated, and here behavior of band gap as a function of number of layers, and some information regarding method of calculation. And from such point of view, utilizing or a little bit knowledge on quantum chemistry calculation may be useful even for experimentator people, because it is many papers, but most of in high reputed journal, that people when discover very interesting phenomena, they ask or collaborate with a group of theoreticians, and they perform calculations. Sometimes a simple calculation you can do very easily, because you know what is a CIF file. It is a special sheet when is all information regarding structure, and it is as a put input information to software, and you choose what you want to obtain and program calculate. Now, it is maybe so easy picture, but for very simple modeling, it is interesting. And you can collaborate with colleagues or groups which not located in your university or another, because they working on internet and send you information also by internet. It is not possible to perform some chemical investigation or some measurements or perform some synthesis online. It is a little bit problem. Okay. Yes. Yes. Today I try discuss with you or share my information, my experience regarding thermoelectric materials. Thermoelectric materials is a special group of materials which have a very interesting possibility. It's able to generate a current after difference between temperature of both sides of element. It is interesting because we have a tool for growing, for generating electricity, which any moving parts. It's only heat. And for example, when I will be a thermoelectric material and came to water, and above my head will be heated by sun, it will be possible when I generate electricity. It is not complicated, but practical application is also not efficient process, because we should understand, when we have a free source will be, and more disturbing us will be situation when we should apply for energy or necessary to exchange such form of heat into electricity. I maybe should complete my lecture, stop lecture here, because it is full information which you should know. It is a well-known phenomena, maybe 200 years, when heating of materials, or gradient of temperature, generating electricity and induce thermoelectric voltage. It is amazing phenomena, but also I think somebody discovered it not intentionally. And now we have many sources of vast heat. For example, steel factory, when we utilizing car, when we have free heat from sun, and you know when you use a lens, you can burn materials, and I'm not able to find for you information, but in USA, some several years ago was grow a steel factory which using sun as a source of for heat. We have a special lens, a special mirrors, and collecting sun energy to burn or melt steel. It is amazing, but it's true. I use a slide from internet. It is a very good company, German company, which is producing excellent equipment. I use especially because such company produce excellent equipment for thermoelectric measurements. It is very preparing many tools for example, DSC, DTI, and for perform measurements, special heat, and thermoelectric properties. It is a big company with a very modern solution, but is not so expensive like similar company in Germany. It was an edge. You probably meet with such equipment, especially for thermogravimetric measurements. DSC is commonly used in laboratories, and such company was a leader. But there were some personal conflict when I grow a new company, and when I go to or visit many laboratories and many equipment of more expensive niche is exchanged by such company. I'm not against such company, but I thought that you like in future working in such subject, it will be interesting to check offer also around such supply. Here, many years ago, I find a very nice animation which show how a system works. Because a system may be working in two ways. One way is generating current through a gradient of temperature, of difference between temperature between end of two side. It is necessary to have so-called end and parties thermoelectric medium. It is a similar like in the semiconductor. It's P and N superconductor. This is some free charge should be to be generate electricity. And also it may be working in different way when we utilizing electricity to cool it. It is you many times emit with a sealant bridge. Yes, it is our tourist bridge when we put it is only fine. It is sufficient to cooling, for example, 20 centigrade below temperature of environmental temperature. We have opportunity utilizing such phenomena in two ways. One for exchanging heat into electricity. Second, we can cooling utilizing the same phenomena, but it is unfortunately consuming electricity. But now is there's a many very useful combination, because, for example, we have such kind of fridge and have a solar panel because energy is not so big, and we have cooling for free. Not freezing, but cooling, utilizing such phenomena. Another, it is not science fiction. Cars utilizing for moving 25% of energy heat from darkness of fuel. It is a sum of friction, but generally Carnot cycle not maybe connected, and we're not able to use 100% of energy, heat energy into mobility. And when you remember some from my previous talk, when I talked about nuclear plants, because nuclear plants is working the same. 75% of heat we broadcasting, but the 25 utilizing for maybe more, because it is a more efficient system, but it is not more than 50%. It is a great problem. How improve it? I think that we have, like, was an idea. We have a car with a covered solar cells, and we not like now looking at place with shadow to put car, and evaporate car, put car on some irradiation to free house. It is a problem of generation. Vast heat is common in all countries, in cold countries and in hot countries like you. It is a great problem because any traditional processes need much of heat, but only some of percent will be used for transforming for mechanical energy or for electricity. And for example, we have some factories, industry, power generation, and all place in such factories generating high temperature heat. Yes, it is a great problem with government. Also, it is some old information that we can make heat organism or preparing heater utilizing only sun energy. And for example, we put to crystal Ganges one as a cooler, and at top we put such heater utilizing sun, and we have a free energy because we utilizing a vast heat. It is also possible, and when you check internet, you probably find many similar solutions which give opportunity boiling water when we are outside. For example, here is information about such generator using almost 16% of sun energy into electricity. Here, it is a very possible application of thermoelectrics in some industry or in some transport of goods of people, etc. Also, we can utilizing thermoelectric devices. We can monitor some processes in industry. Also, it is interesting to here in right corner. Power is not so amazing, free value, yes? But for charge phone or smartphone, it will be sufficient. It is a thermoelectric device on touristic formats. We put some water, some pollution, we burn, and this during heating, charging telephone. We're not looking for a solar panel. We can obtain some electricity in night. It is a practical application of such phenomenon. What is working? For generation of electricity utilizing thermoelectric device, we need two kinds thermoelectric media. It is so-called P-type and N-type. It is easy to obtain during a process of preparation when we put some not matching in valence elements, and we obtain opportunity to make the semiconductor P and I in type. And here we can calculate so-called thermoelectric efficiency, because such efficiency is connected with materials constant, and is connected with temperature range. You know that temperature range is important like spectral range in optical materials. Here, some materials are, for example, not stable when we over temperature, or not efficient. This is connected with three main parameters responsible for efficiency of such device. And when we perform some simplification of such a formula, we can obtain obtain a very simple formula for calculation of efficiency thermoelectric materials. Here we have a three material constant. It is a Seebeck coefficient. It is electric conductivity. It is a thermal conductivity. Here is temperature. And it's quite difficult to obtain or synthesis material which possesses excellent properties, but it is more difficult is tuning such materials. Because when we try to obtain a good thermoelectric materials, we should have materials with a good Seebeck coefficient, because 2 times higher give 4 times more efficiency. Should be big electrical conductivity, but extremely small thermal conductivity. It is difficult to do during one process, because it's a many situation when scientists or engineers try to improve, for example, electrical conductivity, and it's caused that thermal conductivity is 3 times. It is a problem how to do it. It is a many method for improving properties or searching new materials, but it is also one of disadvantages. Mostly such materials which possess very good properties, thermoelectric properties, in composition contain thallium, lead, very rare mercury, cadmium, such heavy elements. Because, as you remember, heavy elements are responsible for a very slow thermal vibration. Heavy elements, slow. Low elements, vibrating faster. And it is a problem of such, because when I have in pocket crystal with a thallium, I quite sad, because the crystal is structure or bonding is occupied. It is very difficult to remove such element from crystals. But problem arises when we start heating material. When we heat material, may stable, more flexible, and a small mechanical interaction may be remove dangerous elements from materials. It is a problem of such. And next situation is connected with some problems with electricity, because we should connect to a system collecting energy, and the system should be temperature resistant also. It is some disadvantages and advantages of such phenomena, but one of them is connected with durability of such solution, and for example, technical solution, how long, for example, when you know that the catalysator in cars have a temperature very high. I don't know, but I think that it is 100,000 centigrade, it is a minimum when we should to burn hazardous elements. And it is a problem regarding efficiency. Okay, when I am producer of expensive car, make a heater or a cooler in cup holder, it is no problem. But for example, when we are like to utilizing thermoelectric energy to lighting, it is not so efficient, because the weight of such device may be over energy yields which we obtain. And from a microscopic point of view, such formula should be more precise when looking like here, because total thermal conductivity is divided in two elements. It is electronic conductivity and lattice thermal conductivity. And it is necessary to remember that, like in thermodynamics, here we use Kelvins, not Celsius scale in calculation. And here is example of one kind of material when such indicator ZE, it is a name figure of Mary, it is behavior connected with a number of charge in material. Yes, it is for transforming charge. Yes, yes. And from such point of view, very important parameters is not maximum figure of Mary, but also is important so-called average figure of Mary, which is a more efficient indicator how compare quality and efficiency of energy transforming, heat transforming into electric. Yes, and it is also a similar situation, because when you obtain for review or read a paper in good journal, it is important maximum of figure of Mary. But when it's narrow, it is not efficient tool for compare efficiency for generating electricity by such interesting from fundamental point of view media, because as we should remember that it is not moving part. And here is some calculation for different materials, how it working as such coefficient. Here, okay, here we have information regarding efficiency of thermoelectric device. We put here two parameters in the account. We put a so-called maximum figure of merit and temperature difference between so-called cold and hot part. And here you see it is a 300 kelvins on the difference give a efficiency up to 10%. It's not so good because it's necessary to look what is it right here. And most typical thermoelectric materials possess maximum of figure of merit circa 1, maybe below 1. It is a most, but we need 350 temperature difference. And here is below 0. It is 8.6% when we start at cold part have 20 centigrade and ZT is 1. It is very difficult to obtain a material, state material with such parameters. Next. Mostly, preparing a single crystalline material is very difficult on such big sizes and very expensive. We never make a model for such. And therefore, people utilizing more most cheap method and most simple method of preparation special elements, active elements of thermoelectric media. It is from nanocrystallitis we grow on powder, and next step we sinter. It is a many method of sintering such materials. I told you about one interesting because it is we have a form for sintering, put a powder, and usually or ambient temperature or high temperature put a force pressure, and we obtain a sintered material. It is also a little bit problem when such kind of materials is stated, because you remember each part of active thermoelectric element working in different temperature. When temperature is differ, also is different size, because it is temperature dependent volume. It is a typical problem. And for example, from such point of view, ceramic thermal superconductors should be frozen only one time. Because when we have a superconductor ceramic origin, when we cool them to gallium temperature or minimum liquid nitrogen temperature, and when we heating, it is some erosion. And from such point of view, in your country, stones and hills not change. But in our country, erosion is very strong. Because in nanoporous came water from rain, and when it's frozen, this volume expands and it is destroyed. And we are not able to see ancient buildings like it is impossible, especially in early Chennai, Pondicherry, where this make houses from one stone. It is amazing, but in our climate it was not exist up to present, because it is maybe a few thousand years. Okay, it is one problem. Second problem is with transporting electricity, because when we have small pieces randomly oriented, and sometimes maybe great problem with electric conductivity. It is very good for heat transfer, because on boulders we have a diffuse of photons, and they not traveling across big distance. And from such point of view, we decreasing thermal conductivity, but also in the same time, we decreasing electrical conductivity. It's one idea how to do it, and very simple, but very useful and very efficient here. It is so-called mosaic crystals. We put, when we have a powder collector, we put strong electric field, we align crystals and flexi separate. And very strong person, which is German origin, but after complete PhD working in USA, Professor Schneider, they published article when for cuprum, telluride, and sulfur, because with different composition, they firstly perform measurements for ordinary citadel, normal citadel, and later try to utilizing the so-called mosaic crystal. We align them in one direction nanocrystallites, and next we will measure, and obtain almost 4 times increasing of figure of that. Such material is not good for application, because, as you see, maximum is big, but range of temperature also is big, but most of temperature range ZT is below 0 point. It is good for publication because here maximum of ZT over 2. It is a very excellent coefficient. What is also is a problem? It is mostly binary crystals and very not stable and very also possess a degradation process during work. But also, you should know that most of halcogenide material is have a very slow stability in atmosphere. But here we also have additional disadvantages with this high temperature and gradient of temperature. But the result is amazing. We can adopt or remember it that such method exists because in many another when thermoelectric application may be used. I also, when I should not remember, to not forget, show you a link with one laboratory in Poland when they applied extremely high pressure for CTEC. They not only make a mosaic crystal, but also have opportunity to apply extremely high pressure. Now, many groups perform experiment when they like to obtain a transparent ceramic from Poland. And I seen some preliminary results. It is very promising. In slide maybe in the afternoon, I attach information about such laboratory because when some of you will be working in non-organic crystals or materials or powders, it will be useful for preparing new materials. Okay. Here is some information regarding how willing to obtain very good thermoelectric materials. It is connected with a comparison of experience and physics of materials. What is it required to preparing a good thermoelectric material? It is heavy atoms we discussed about, high dielectric constant and low effective mass. It is important for high carrier mobility. It is when we have a good signal, yes, for assumption. Multivariate band structure and high band degeneration. It is improving electrical conductivity. Small band gap, but not so small gap, because it is connected with improving carrier concentration and no bipolar conduction. High solidity of dopants, possible to optimize the carrier concentration to reach a highest power factor. I also give you information regarding very good laboratory in Poland. It's focused on thermoelectric materials, because sometimes when you have materials and check in literature that such materials may be good, for example, thermoelectric, you don't worry. It's necessarily send to email with information that Professor, I have such crystals from literature. I know that it is may be possible good thermoelectric. Please check it, and when will be interesting results, we write a joint publication. It is typical, and don't worry in the future when you have some information. It is not only connected with thermoelectric. There is many people also from your country make a start vegetarian because they're not afraid and sent to famous laboratory in Japan, Germany, or another country to perform some very rare measurements. It is for performing thermoelectric measurements. Idea is very simple, but practice is a little bit complicated. And in the second part of my talk, I talk about a story with my first thermoelectric materials, but which change mentality in people working in such topic. And here is interesting for future, but what is it? Last, I saw a bit of dopants. Such group about alcohol, Michael will not take from your crystals because they kill us and because they contain much of darkness. But I checked one paper published in prestigious journal, small letters, we put 2% of time to increase mobility of targets. And also, it is possible utilizing quantum chemistry calculation to check or to predict possible properties of particular materials to confirm or next thermoelectric property. It is many method to increasing electric conductivity without mutual increasing thermal conductivity, because we like buy something and not spend money. Yes, it is like it is some method how do it to keep low thermal conductivity, but try to improve quality of electric conductivity. And also, as such, cuprum basalt diamond-like halogenide also possess very good properties and possess quite low thermal conductivity. But it is not good challenge, but it is example how a procedure should be done. And also, binary material. It is very good for thermoelectric material, and also possess quite new, quite low thermal conductivity, but good zinc T is a connected not by low thermal conductivity, but by the high so-called power factor, because as Seebeck squared multiplied by sigma electric conductivity, it is a name of such coefficient. It's a power factor because it is connected with the power is decreasing by thermal conductivity. Okay. Here we have also next example when was tested mechanism to improving electric conductivity without enhancing thermal conductivity. This is also some method of controlled introduction of defects in materials also give good results. And here we have some remarks regarding improve some thermoelectric materials properties, and it is connected with topics which we discussed. When we transform on microscopic language such yields which we obtain during our discussion, we should to obtain good material, reduce phonon main free path, reduce phonon group velocity, reduce phonon heat capacity. And some of such parameters is very easy to measure, perform measurement. And from such point of view, when we have a detailed investigation of material without performing difficult thermoelectric measurements, we can predict if a particular material may be good material for thermoelectrics. And special kind of thermoelectric materials which possess extremely low thermal conductivity is so-called thermoelectric under glass link. And research is very simple, but it's difficult to do it. And here is some road how do it. It is, for example, field of work of nanotechnology when we make a textured structure to avoid free of long path, free on path for phonons. And also we have different possibilities how improve such materials properties. And I don't know. Okay. And here is some figure of many different kind of materials. When you look for such very complicated figures, it is difficult to find some materials, good materials, which are not chalcogenide materials. You see in left top graph, we have some oxide, but figure of Lewis coefficient connected with efficiency is not so big. And most of them contain not good for health elements, hazardous elements. Most of them are not stable, but some classic materials is in practical use do a small efficiency, and such materials also are useful for different applications. And we would like to make a break. A few minutes, we take a break, and after I complete our lecture, 40 minutes is maximum. We complete on time. Thank you for your attention. Such very simple binary materials became a very good thermoelectric when we take account only formal parameters, because possess high ZT, possess very good behavior of such temperature behavior, but is unfortunately not stable material. But from possible application, such discovery of such materials and very high properties, thermoelectric properties of materials, put attention for so-called cuprum-based materials, and many groups start improving properties of such materials. So here, such very simple binary material possess quite low, because below 1 millivolt per Kelvin thermal conductivity, and do a not so big power factor, possess a very good ZT, because ZT as such parameters is almost 1.5. It is big materials, but it was a focus for different research. It was many articles and many reports from measurement when people early perform dielectric measurements of some thermal crystals. It was agrodinous structure. It was cuprum 7 phosphor selenium 6. Such material was investigated in many articles, but for a long time not to be considered as thermoelectric materials. And with my group from Ukraine, we put interest for so-called solid electronics, and my collaborators grow some single crystals which possess a structure like investigated previous materials. We, at first attempt, preparing classical ternary materials, except selenium. We also prepare material with crystal with sulfur and perform some measurements like photoconductivity and mobility, etc. And one of methods of improving materials properties is maximizing so-called configuration entropy. It is, we can do it by add some additional elements to compounds with keeping the same crystal structure. And utilizing such strategy, we able to continue work of Professor Jennifer Schneider. It is his group which performing first thermoelectric measurements. They perform measurements of such crystals and discover very high copper-ionic mobility and extremely, for such time, thermal conductivity, because interest of such materials was not from possible application, but investigation of mechanism of conductivity. And some of different group start work on improving materials properties, thermoelectrical efficiency, because such material possess maximum figure of merit 0.3. It is very low, but it was great discovery investigate thermal conductivity of such materials, but thermal conductivity was extremely low. And what is disadvantages of such materials? Disadvantages of such materials was a very small electrical conductivity, because it was a worse parameter among typical value of CBEC and thermal conductivity, because thermal conductivity was excellent because it was very small. And what people do? Why we should improve electric conductivity? We have two ideas. One, we improve or change cationic bond. Some ions of cuprum we substitute by silver. It is one. Second attempt, we manage anionic part. And what is the idea? We selenium should substitute dielectric sulfur or more metallic tellurium. They choose second, at least. They some substitute some selenium by tellurium and obtain quite good results because we strictly improved thermal conductivity. Here is just not a figure of merit because power factor was quite good, thermal conductivity not change, and finally they improve such materials, obtain a better figure of merit, maximum up maybe 15%, 15% maybe. And for a long time, nobody interested such materials. When I obtained information and during seminar, we discussed with colleagues what that such materials may be interesting, we decide that we make a different decision when such group. We improve, try improve materials properties, substituting by sulfur. It was, from his point of view, a crazy idea, because people thought you kill electric conductivity. But we thought we grow such crystals because it was for a different purpose, and we try to perform measurements. It was also interesting that in opposite to all previous measurements, we able to grow single crystals. And what is the advantages of single crystals in comparison to modeling? Advantages is that when we perform quantum calculation, quantum chemistry calculation, mostly we consider that our sample is a monocrystalline. When we have some, especially when we calculate the transport properties, etc., predict, it is more easy when we should take account diffuse transmission on different direction, etc., etc. Performing thermoelectric measurements for single crystals also give some interesting results, because some crystals possess thermoelectric properties different in different directions. It is an anisotropy of thermoelectric properties. It is also interesting from fundamental quantum. But what is the advantages of such materials? Advantages is chemical composition. All materials is maybe environmental friendly, because in comparison to lead, cadmium, and other, sulfur is quite sound. And we try to grow such crystals which so-called belong to groups of argondorylida. Yes, and we utilizing for grow single crystal very expensive compound. Expensive because it was high purity, because for single crystal grow is necessary to utilizing high quality ingredients. when we try to make polycrystalline samples, it is not obligatory. And also, as such, crystals is well known over structural phase transition. And also, a temperature of structural phase transition manifesting not only with under crystallographic measurements, but also by properties. I spent more than half of my life to investigate phase transition, and because it is my scientific hobby to investigate phase transition and explain why particular material of phase transition. Here was also, as you remember, I yesterday showed also sequence of bromide crystals when we change it anionic part and make a structural phase transition. Here is the same. Probably is okay. We perform several samples with a different mutual composition, sulfur and selenium. Here, it is lattice constant as a function of mutual composition. When it's linear, it is doesn't mind what crystals are a good quality because it is fulfills so-called Vega collapse. It is connected when we smoothly change composition and exchange a smaller atom ion by higher in more concentration, it is results. Here, also we able to check how percent of sample possess behavior 1 loop or second phases. It is like a solid solution between single crystal with sulfur or selenium. It is okay. Also, is interesting measurement. This interesting measurement because most of all measurements we perform on not on single crystals because it was a little bit difficult, but utilizing polycrystalline samples which were simple. And you sometimes use for detecting morphology, for example, sand. Yes, you make sand measurements or make, for example, Raman testing. We can utilizing different tools for investigate homogeneity of materials and morphology. And here we utilizing as an indicator Seebeck coefficient. Seebeck coefficient was measured in range 3 for 3 millimeters. And it was one color, different of colors seems that it is some unhomogeneous materials, but from in compared to another materials which we investigate early, it is a very good quality. And we have opportunity to check morphology, not only utilizing sand, but also utilizing more sophisticated tool. And what was happened next? Next, we perform some typical measurements. We also calculate configurational entropy here and see the coefficient, how maximum changing with chemical composition. We make a study which we like understand why materials properties depend on chemical composition. It was our idea, and also we like to check if a principle that maximum configurational entropy determining good desired properties, here is one's high temperature, may be validated in next steps. Here is between circa equal composition content of selenium and sulfur give a maximum of configurational entropy. And we perform some measurements, perform some measurements. Here is a power factor, ZT, and here for particular combination, it was 50-50. We obtained in tracing figure of merit 2 times, from 0.3 for selenium, for 0.40 for with tellurium. It is a previous measurement, another group, and when we substitute Worm's element, that is a sulfur, for improving electric conductivity, we obtain 2 times more efficiency of thermoelectric thermal properties. But also it's interesting because my young collaborator performed calculation regarding expenses of ingredients and such elements, and it was all good and cheap. It was a great interest, but it is not end of story, because after publishing our papers, a huge attempt was focused on investigation origin of extremely low conductivity, because PA's conductivity was 10 times more in previously best thermoelectric materials with low thermal conductivity. And it was a huge papers. I counted 5 or 6 papers which was published for explaining extraordinary low thermal conductivity. And for us it is interesting, but I know myself when I not like check such theoretical prediction, and recently we perform a special kind of sophisticated measurements of phonon structure utilizing synchrotron. This method is very simple. It is between reflection in infrared spectral range because we using radiation with energy 0.02 electron volt. It's a very fine method for investigation, and also what's very important, spectral range, because we have opportunity to perform behavior, second vibration of particular heavy-ion with a spectral range which is not available for ordinary laboratory instrument. And now we complete a manuscript in such form. But such phenomena was very interesting because such articles were published. It was published, for example, Advanced Functional Materials Science, etc. And I think topics is very hot for people working in thermoelectric materials. It was sometimes people ask me why you probably participate in many conferences in thermoelectric. I was only one. Then invited talk, deliver lecture regarding such topics, and next many laboratories start working on similar materials, perform synthesis, but also with such materials is one unpleasant job, because one of crystals possess huge dimension, and we try to perform measurements utilizing not separate sample, but single crystal. But one PhD student change Kelvin with Celsius and bag samples to measurements. But one result was amazing because from quantum chemistry calculation, people predict that measured Seebeck was circa 300. But from quantum chemistry calculation, they evaluate that should be between 5 and 600. I obtained a little bit of data, and it was more than 700. It was a difference. Maybe thermal conductivity will be higher, but for me it was perform a calculation and compare with results for sputter or synthesis samples and single crystals, because it is also interesting for testing measurement, because when you have a well prepared material, very good and accurate measurements, you can compare with a calculation. When you have, for example, 6 samples and a calculation precision, because it is a many possibilities working well, you can confirm that your equipment, that your method of calculation is valid for materials which not be synthesized up to present. And for example, we can perform some measurements and perform calculation, and people maybe believe when they synthesize such materials, properties will be agree with our previous measurements. And I hope it is end of such thermoelectric story, and also is information that when you have sometimes a good idea or you're not working in subject which, for example, your samples may be also interesting, your material may be interesting, don't worry, start collaborate with people which focus on something. They have equipment, they have experience, they perform measurements, idea is yours. You are also co-author of publication, but you can have additional experience, except experience on purpose what you preparing yourself. This also I would like to convey to you some my remarks, my experience, how is the behavior of people which doing science. It was many situation, for example, when I was a reviewer of article, and remember that people working in particular science or have special samples and pitch to them. Later, the professor, I interested because you publish an article, I don't do it before he published it, yes, because it is not public information. It's also possible. You don't have right to contact another people, another group, but it is important to give a real idea of collaboration. And maybe it is time for lunch, yes? Thank you for your attention, and we meet evening. Yes, but you're preparing something, yes? Yes, when you have some idea, some topics, please prepare it on maybe electronic version. We also put on ekran and we will be discussing. Because we have today and tomorrow a such lecture when you should actively participate. And when you have some idea, it is possibility to show idea, and we all will be evaluate such idea or discuss or try understand or maybe give some remarks because maybe somebody meet with a similar problem or know somebody which perform such measurements. You should start collaborate as a team. And I think that after such course, we also exchange some emails between you. Also, mine is not secret. And when you have some opportunity to collaborate, don't worry. And it is when you are working, for example, with a special subject, it is very important to discuss with your supervisor. It is possible to contact with professor. Maybe he establish contact and you can opportunity to go. It is doing science is also like with electron in conducting band. It is necessarily involved. Yes, because when you sit in place and not contact with our outside, it's difficult. We're not working in Project Manhattan. You remember, yes? Project Manhattan. When the people was elected. But now is thank you.
Yeah, good afternoon, everyone. So, for the last 2 days, I think we are seeing under one of the topics. Today's topic, I think, from the last 2.5 days, we are seeing different concepts about the concepts like what we call like multifunctional nanomaterials and other light photo catalytic single crystals and all those concepts. But as I'm not a physics, I'm related to mechanical. So I don't talk on more on physics. Okay. So I'll talk on more little bit. My area is on composites. So I'll start with composites and then relate those with nanocomposites, nanomaterials. Probably I think already Professor Ajim sir already explained about nanomaterials and other fabrication techniques. And you might have yesterday already you have seen the fabrication of nanomaterials. So I don't want to stress on those concepts. So I'll talk on materials, composites and nanomaterials. So my lecture starts with introduction of materials. Probably I think earlier speakers or else you have already studied about it. I'll start with the materials. I'll take you through like evolution of materials, how it is started, and after that materials how modified to newer generations, and what right now what kind of materials we are using, and how the advancements are happening in the materials in terms of nanomaterials. So this is outlines like introduction of materials, composites, nanomaterials, fabrication of composites, and then fabrication of nanomaterials, and a little bit characterization of the topics. So first I'll say like classification of materials. Everybody have a thought like classification of materials starts with engineering materials. We start with ferrous, non-ferrous, composites, plastics. So all these are general classifications. But I'll start with this slide. It shows like the materials are starts with two kinds. One is man-made materials. Another one is natural materials. These are natural materials. In the nature, we have a different kind of materials. Few materials modified by a man and then developed the materials. Whatever we studied, like for example metals, polymers, ceramics, all these are man-made materials. These are not directly available in terms of metals. For example, let us take any kind of a metal, it is not available in terms of a direct metal. Like for example, aluminum, iron, all those. These are available in terms of ores in nature. So we do some process, we extract them, and we develop materials. So that's why all these called man-made materials. This polymers, ceramics, metals, and natural materials. What are the different natural metals which are available in nature? So in the nature we have mud and clay. We don't do any kind of a processing which are available in the nature. These stones, skins, wood materials. In wood, different kinds of woods we have. Softwood, hardwood, different kind of plants. So all these kind of natural materials. So why I start this slide, the topic with this slide is, from the ancient time we have materials. We used that materials. Once the civilization started, we changed the materials. Nowadays again there is a boom like go for natural materials, use natural materials, reduce plastic, don't use plastic, all these things. Means again we are seeing towards the nature. So that's why I start with the slide with the natural materials and man-made materials. So this slide generally everybody sees whenever you study any materials concept. We'll start with this slide. Like we have metals, plastics, ceramics and composites. Whenever I talk about composites, I'll show this slide and then combine the concepts. For example, metals, we have ferrous, non-ferrous, amorphous. I don't talk about the more about the classification related to it. So these particular metals combined with plastics, like a metals in terms of a powders, combined with the plastic forms a composite. That's called metal matrix or metal filler polymer composites. Later we'll talk about more about that. And these plastics combined with ceramics, either the oxides or carbides or any other materials in a powder format. If you mix into polymers, either maybe either thermoplastics or thermosets, we get composites. Okay. So combining metals and plastics or plastics and ceramics or metals and ceramics gives you composites. The third one, last one. So what is composite actually? It's not a new one. Before going to that, so how you understand a material? What are the basic things to understand a material? Like for example, there are n number of materials. Earlier slide I said natural materials, man-made materials. We have different kinds of materials. Right? So to understand the material, what we need to know? We need to know the properties. So we need to know the properties, like properties of the materials. As I'm a mechanical guy, so I show first one is a mechanical properties because my field, right? So I show mechanical properties. Generally, everybody studies physics. So generally starts with physics. Okay. So physical properties we have, and after that chemistry will run more. So chemical properties. From the schooling we do that. Physics, chemistry, these are the two, and biological properties. In metals we don't do more biology. Okay. So physics, chemistry. After that comes to mechanical. This integral part of this physics and chemistry comes to mechanical. And there are other fields. If people are from the different fields like tribology, some other category. All these properties, once you know all these properties, then we understand the material better. Any material, if you understand all these properties, then we can understand that material. We have a n number of materials. For each and every material, if you start learning all these properties, it's a very difficult. And comparing the properties and then correlating it, this will be very difficult. So these are the few properties to understand mechanical, like strength, toughness, hardness, ductility, elasticity, fatigue and creep, physical properties, density, hardness, and other thermal conductivity, all those properties. And chemical oxidation, corrosion, these are the terms. A few more. Coming to composites, why composites? Because as a topic is about composites, I slightly jumping into the composite materials, not talking more about other kind of material, because the concept is about nanomaterials. If you start talking about materials and then their properties, their classifications, then the class will end. So I directly jump into composites. Particularly first, why, what fundamentals are required, how composites are different from other engineering materials, and what constituents are presented in that composites, what are the different constituents present inside it. Because we have metals, we have plastics, we have ceramics, then why composites? What are the other constituents? How it is prepared? What are the advanced technologies in the composites? And how composites are manufactured. So these are the topics, terms. If you understand this, then we can understand the composite easily. But up to now, I didn't say about what is the definition of a composite. What are the terms inside the composite? So we'll go to that. Before that, as I said, material evolution. I'll start with the material evolution, right? So I just given a graph. This is taken from online. So I started with 10,000 BC and the present 2020. So this graph shows you 10,000 BC to present, right? What are the materials? How the materials are evolved. If you see the graphs, I talk with first one metals. As I said, in the ancient time, 10,000 BC also we have metals. Then that time also we have metals. The first one what we have is a gold. Nowadays it's a very costly one. Among all the metals, if you see, we can purchase a gold because it is very costly. But at that time, the first metal what we have is a gold. People start developing different components with the gold. The disadvantage with the gold is it a brittle or ductile? It's a ductile. If it is a ductile, easily it will bend. For structural applications, for other applications, we can't use it. So people start develop a gold. There is no applications. They start seeing other materials. In 5000 BC, after 5000 years, they develop copper. They start using copper. Copper is also, it's a ductile, but when compared to gold, it's somewhat harder. When compared to gold, it will be somewhat harder as a copper. They developed copper, after that bronze. Finally, they identified iron. Once the iron comes, all the structures, all the materials, and the entire world, it is changed with iron. Because they had earlier used with the bronze. In any old movies, if you see it, all the components in the bronze only they show. Olden movies. Some, if it is not old movie, somewhat related to some 90s or something, they'll show more iron kind of things. Aluminum, iron, all those things. So iron comes in the picture. After that, we have a cast iron, steels, alloys. After this, we have more alloys here. Present when this is a plant, we don't have more metals. Why we don't have more metal means there is an industrial revolution. that industrial revolution starts changing the metals. Whatever the metals we have, people start changing the metals because the weight of the material is high. So therefore, one small question here, like why this material is changed, what is the need? For example, simply we will take one example, how this particularly aerospace is modified. If you take like when I started like 20 years, 15 years back, when you want to go to from Hyderabad to Delhi, the aeroplane cost is high, travel distance. The distance and in the aeroplane the cost of the ticket is high. There are few reasons. Number of passengers will be less and fuel consumption, all those parameters are there. Nowadays it's become very less. That days 20,000, now it is 2,000, 2,000, 3,000. So the distance is same, the flying heights are same, everything is same. Only thing modified is materials. Earlier we have full metals, now we have full composites. So all the aero structures are modified with the composites. Composites are the lightweight materials. Due to that, fuel consumption reduced and maintenance reduced, aeroplane cost reduced, finally ticket cost reduced. So this is the logic. So the materials are evolved from metals to polymers. So next concept is about polymers. Again, polymers are not a new materials. These polymers from the ancient time we have. There are wood materials, skins, leathers, all those things. Ancient time we have it. After that, people didn't use anything. They use only glues, some kind of gum. After that, rubber. Up to 90s, 1900, we don't have anything, particularly polymers. In 1940, when there is a Second World War, people start using plastics. In the First World War, they used metals. In the Second World War, they used plastics because there is a radar technology that time identified, and then to they don't make detection, they use polymers. They developed polymers. So they start using polymers. From that day today, we are using more plastics, polymers. So we have, you can see it from here to here, all are plastics. Nowadays also we are using more plastics. Only one concept is, nowadays there is a slogan like reduce plastic and don't use plastic, all those things are coming. Next one is composites, our topic, what I am discussing now. So the composites also not a new one. From ancient time we have, if we have a plant, the plant is a composite. Our human body is a composite, but we don't know the terms. Okay. So these particular plastics composites we have. After that, in the entire line you can see there is no composites. In 1940s, at the time of Second World War, they developed GRPs, glass fiber reinforced composites. They use plastics, glass fibers to develop the structures, aerostructures. They use it for the aeroplanes, for a fight, Second World War. So that time they used it. After war, again they continuously they are not doing the warfare. So what they have done is they shifted to industrial revolution. They changed all the metals with the plastics and composites. Nowadays, if you see any high-end cars, high-end equipment, all there we have a carbon fiber composites or glass fiber composites or Kevlar fiber composites. So about composites and ceramics, from ancient time we have different materials. So coming to this evolution, simply in the diagram like I give an AI, ChatGPT, like to give a evolution of a materials, it gives like this. It shows like a Stone Age we used a wood and stone. You can see it here. This is not a iron, this is a stone. If you see the old movies, that time they'll take a long stick and then on the corner they'll fix a stone. They wrap it. That's what they given in 10,000 BC. It's a Stone Age. They use stone. After that, Bronze Age, they use bronze. After that, Iron Age, they used iron, the hammers and all those things. Nowadays, polymers, we are using more plastics. In the future, we are going for composites. So in that, it assumed and then given an image from 10,000 to present time. Okay. And ancient side, like I said, like what are the ancient composites? What exactly it will give? It shows mud straw bricks. If you see the history, I think everybody in the movies are real. You might have seen it like Colosseum or Roman culture. They constructed a long back, almost thousands of years. Their buildings are intact. What is the construction, particularly what we have in our India, in our other parts? We have our houses, our buildings, whatever building we are sitting now, it's hardly, it will be 100 years. Why this is 100 years? Where we have iron, stones, and the construction cost is high, everything is high. But their construction in their olden ages, they don't have technology, they don't have anything. But their constructions are still remains. What is the difference actually is, their bricks, whatever the construction they use, this mud straw bricks, they consist of 9 to 10 different kind of materials. If you see the crack propagation or any techniques related to mechanical terms, so for example in the failure, if any crack started, the materials which are having a new thing, it stops the crack propagation. It won't allow it to deviate, it allow it to break. So that materials, 9 or 10 materials, won't allow it to degrade very faster. That's why that particular structures still also we have. Our structures, whatever the cement bricks what we have, or normal bricks we have 1 or 2 materials. If one material have the crack has a capacity to break it, the entire structure will be gone. So other things, pottery and then wood, the wheel concept. I think if you are interested, you can see the wheel concept. When the wheel is evolved, nowadays whatever the components, whatever the equipment we have, transportation, everything, that depends upon the wheel concept. Once they develop the wheel, they will get. And finally the mud, the bricks. For a real image, this is 13,000 BC Egyptian technology, they used this bricks. Right now also we can see it. In Egypt still it is there. It is not decomposed, it is still in there. And in 12,000 AD, and jumping directly to Egyptian to Mongolian culture, they used a bow. That time, nowadays if you develop a bow, arrows or anything, with all the technologies, we can't send an arrow for almost 1 kilometer. That time, they don't have all the technologies. They structured this bow and they developed the bow. To develop that single bow, it takes almost 1 year. So they use 9 to 10 different kind of bamboos and other materials for that, and they developed this bow. That's why the popular, like if you see any Mongolian works, they use only bows, arrows. Okay. So that is one of the composite. That time they don't know the word of composite, but they developed it. This is I said like evolution of materials at the time of Second World War. In the World War, you can see these structures. In the First World War, those are iron. They developed with the plastics. After that, they used it for putting the bombs in the different places. They used it for a war. And simply I have given like evolution how it happens. 1940s we have a woods and fabrics. 1940s to 1960s we have a low carbon alloys and other materials. 70s and 90s we have again fiber glasses and alloys and carbon composites, natural fiber composites, now nano composites. So with this, like some few examples, like what are the day-to-day applications what we have, exactly like in a day-to-day life what we can see related to composites, like concrete, straw bricks, wood and everything. Why particularly these composites are necessary? What is the use of it? Why we need to use it? In this particularly it have a high strength, high stiffness. These are the different properties which differ these composites with the other materials. So again, the definition of a composite. I think everybody knows alloy. Have you heard the word alloy? Alloy means, generally the definition says combination of two or more metals to form a material, a new material. In the composite, the definition is same. It's a combination of two or more materials or metals. Then what will be the difference between an alloy and a composite? Here comes like, if an alloy is, if you combine two metals, you form a new alloy which having a new properties, the entire material will be a new material. When it comes to a composite, two materials will be joined together. They don't lose their original properties. They act as a single material. We can easily separate it. Once an alloy is formed, then we can't separate it. We can't separate that material, alloy. But when it comes to the composite, when two materials are combined and form a new structure, that particular structure can be separated easily. So that's the difference. Again, this same like history of composites is given. And types, we have polymers, metals, ceramics, and natural fibers. And here in this picture, you can see it. We have a reinforcement. These are the reinforcement, and this is a full matrix. To understand composites, I hope like few are already working on it. Few probably these words will be a new things. So if I ask you like any example for a composite, let us say one example. Generally in the class I will say regularly. Everybody see cricket, right? Everybody see cricket, play cricket. Majority of the people. So when you see the bat, if it is a two halves, one is a handle, another one is a bottom, one is a bat. If two halves is separated, then how we can fix it? Handle and the other halves, two halves is separated, then how we can fix that? Gum. Okay, one option, what is it? It's a gum. Where is gum? Anything? Any other? Nails. He said nails. We can fix a nails and then read nails. Okay. Any other? Threading. Directly we will put threads. Threads and vehicles. Okay. Any other? Any other things?
And we make an incision on the body of the bat and we try to fix it instead.
Fix it in?
Fix the handle in back inside the body.
Ah.
We make an incision, like
Okay.
something like an arrow or something that stays. And we stick it
Stick it with what?
with gum.
Gum. Any other? Fine. Now we have different answers. Let's come with one by one. Someone said gum. We'll fix the two halves and put a gum. Now the problem with that is gum having a less resistance. When you start again playing it, whatever the ball with a different speed hits the bat, because you are sending your energy right to hit it, then your energy is sending through your body, and the opposite side ball is coming with a speed. Once it hit the bat with your energy, it's opposite reaction. The two will be separated because that particular gum won't have that strength. Now the gum concept is gone. We can't use a single gum. Next one, someone did nails. If you fix the nails also, that nails already damages the surface. Surface damages the handle as well as damages the bat. When two are damaged, then we can't use it. Next, someone said we can use threads as well as gum. So here, if you use the threads, if you roll all the threads on the top of a bat, on the handle, and pour the gum, equal portion, then gum will be in a liquid state and the threads are in a dry state. These two will be bonded together and these two will roll on the handle and the bat, join these two halves. Then whatever load you are transferring, you transfer to the threads with the handle, and that is already connected to the lower bat, and these two are bonded with the Fevicol and threads. So the load transformation won't happen through the polymer gum. It transfers through the threads. All the threads act as a reinforcement and the load is transferred to the lower bat. It never separates. So here in the concept, if you want to separate it, put in a water, the gum will again convert into a gum. It will be liquid, come out, all the threads will come out. So this composite, the combination of threads and gum make you a composite. These can be separated easily and can join together easily. Okay. So only thing is these threads are reinforcements, gum is a matrix material. So in a composite we have reinforcement and a matrix. Matrix always, the matrix always transfer the load. It won't carry the load. It always transfers from one body to another body. Reinforcements always carry the load. The reinforcements are the threads, matrix are the Fevicol. So Fevicol always transfer the load and these reinforcements carry the load. So whatever the load which we apply, that always carried by the reinforcements. Okay. So that's why in this image you can see it, there are two phase matrix and reinforcement. The reinforcements always carry the load, matrix always transfers the load in between the reinforcements. What are the different types of matrix we have? Quickly I am going like, because as we have the nano composite, later we come to that topic. So we spend more time on the nanomaterials, nanocomposites, less on composites. Because if I directly start to nanocomposites, if you don't know composites, then there is no use because you don't understand that concept. So bringing to first metals. If you use metals as a matrix, we call it metal matrix. If you use polymers, polymer matrix. If you use ceramics, ceramic matrix. So in all these three, we can add a new material as a reinforcement. Because sometimes like these metals won't have a high strength. There we need to add some materials which can modify their properties. For example, let us take aluminum. Aluminum is a ductile or brittle? Aluminum is a ductile material. So what about the hardness? Is it a higher or lower? The hardness of aluminum, it will be lower. So if I want to increase the hardness, then what I can do? To increase the hardness of aluminum, what we can do?
Add another.
I think there are some few treatments, like for example, like a quenching, heat the material to the higher temperature, put it in the water, so that oxides will form on the top surface, which changes the properties, increase the hardness. That's the one concept. But what we are doing is, we are spoiling the entire material, we are changing into oxide. The aluminum is converted into aluminum oxide, we are changing the material. Instead of that, if you add only a coating of a top of layer, add a ceramic coating on the top surface, where particularly the surface will be modified. Then it is called a composite, surface composites. On the top surface of a single layer, we just inserted silicon carbide particles. On the top surface, it will be modified. Then the hardness we don't get for the aluminum. The hardness we got for the ceramics, composites, SiC. Silicon carbide is inserted on the top surface. That top surface gives you a more hardness. Hardness is increased for it. So on the particular location only, we are increasing the hardness. If we need a hardness in the entire composite, then what we do is we develop a full composite, not only on the surface. If you need only surface, we develop surface composites. If you need a full, we insert all the particles inside it. So in the metals, if you need increased properties, we add some other materials. In the polymers, if you want to increase same concept, we add some other materials, either continuous fibers, glass fibers, carbon fibers, different kind of materials we add, and we can do it. And ceramics also same. How many of you seen like Formula 1 cars? F1 race. So is it a metal car or what kind of a car it is? It's a metal material. Carbon fiber reinforced. What will be the approximate cost of it? Billions in terms of crores, like 1 crore, 2 crore?
No, sir. Around
100 crores.
Yes, sir.
I don't know if it is 100 crores, nobody participate in the race, like where damage is 100 crores done. Now, like when you see a Formula 1 race, when it is going on a track, sometimes it will call means 100 crores done.
Yes, sir.
The prize won't give you 100 crores, right?
Yes.
If you win the F1 race, they won't give you 100 crores.
No, sir.
Then why do like I'll take a 100 crores vehicle and then spoil it and then I'll take a 50 crores.
Sir, they are building a technology.
No, it's not a technology. Actually, that racer cars also it comes of 5 crores, 10 crores. It's not like 100 crores. Because the prize money is not 100 crores. Whatever the prize money they will keep it, it won't be 100 crores. Because the carbon fibers, what we get, for example, okay, maybe some vehicles, if they go for a higher end, there maybe it's not 100 crores. If 100 crores, nobody will participate in the race. Okay. For example, if you see like, if I say like, we don't talk about like racer cars. If I say bicycle is 10 lakhs. You keep it outside. Don't sit here, right? Because cycle is outside, which is 10 lakhs. If I sit here, then my mind is there only, right? There are 10 lakhs, kya ho gaya, like bar hai. Okay, I don't sit here. Even if I put a lock also, I'll always think. Because somebody will carry it, right? It may be 10 lakhs means very light. You will take it and go out, then 10 lakhs there. Then imagine like if it is 100 crores, press me okay? So that's a 5 crores. That is a 5 or 10 crores. So if you say that 5 crores, the weight of that particular racer is very less. That's why it moves very faster. High speed. When you go high speed, there is a drag, there is a high friction that can need to be sustained in that high speed. So for that you need a high strength materials. So they use carbon fibers. So the cost increases as you use more quality carbon fiber materials. Okay, for the composites. So we combine different materials. This is, as I said, like every time if I said a glass, Everybody confuses what is a glass because from the maybe yesterday or earlier he is talking about crystals and all those things. Probably I thought like if I said glass, you think about that glass. This glass is different. Whatever the glass, what you crystals, all those things are different. This is different. But this is same, similar glass, E glass, S glass. This glass is extracted from that material. So the extraction process is, this one. Melt the glass. I think many are working on bioglasses. Melt the glass, extract the fibers, and make this kind of mats. It's a bidirectional or unidirectional mats we develop using that glass, extracting a thin fibers from the molten material and prepare this. The strength of these fibers are, it's around 3200 megapascals. If you see any kind of a metal won't give you 3200 megapascal, any metal. This gives you that, but as an individual. If you combine it with some other thing, it will be gone. Means it's like our shirt. If I wear a shirt with that material, fine. If I want to apply any kind of a load, it won't sustain that because it won't have stiffness and other properties, mechanical terms. So I need to combine with some other thing, some other polymer, some other metal or some other material. When I combine it, it won't give you 3000. It will give you 300. So that's why we don't have more that. And it will be very less cost. These are carbon fibers. Again the same thing. As I said, racer cars and all those high-end applications, we use this particular carbon fibers. This particular low grade carbon fibers gives you per meter 3000. Okay. If it is a per meter 3000, if I want to make a plate of a metal of a 10 layers, then assume it will be 30,000. If I want to test it for it, then it goes in terms of lakhs. For a glass fiber, it is 100 rupees nowadays. We can go for any kind of n number of materials, we can test it because the cost is low. Okay. So this gives you around 6,000 megapascals. So you can imagine like a glass fiber 3000, it gives you 6,000, means double of it. That's why for racer cars, for high-end applications, for space applications, they are using this one, carbon fibers. Okay. Have you heard a bicycle costs you around 50 lakhs, 60 lakhs? Have you heard about a cycle? Cycle costs you 50 lakhs. So in that, they use this kind of a high-end carbon fibers with the 3 pegs. Directly they will make a single structure with the carbon fibers. The entire cycle will be a single structure. So that's why the cost will be very high. You can lift it with a single finger. The entire cycle you can lift with a finger. That much lightweight. That will they use it for racing cycles. They need a high strength with a lightweight. They use for that. Okay. So again, classification just for idea is just giving it. How the fibers can be layered. Unidirectional, bidirectional, multidirectional. Why we go for multidirectional? Because as a mechanical, we'll see like there will be a dynamic load. For example, if I am moving, different kinds of loads will come. For example, when I am walking, friction will develop below my feet, air will hits me, and some other forces from other direction. So dynamic loads happens on my body. So if I develop a material with a multi-directional one, then it can sustain for. For example, if I have any only friction is I'm talking about like on the lower, when I'm walking, only I talk about friction, then I'll go with one directional materials because only one condition. When I talk about the air, some other loading conditions, all those parameters, then I need to go for a multi-directional. That's why in the technology, in the terms, when we change the concepts, we develop new materials like multi-directional materials. Okay. So how many of you heard about functional graded materials? I think you don't have it. Others, can you raise your hand? You raise your hand. Like how many of you heard functional graded materials and a short form FGMs? No. Okay. Smart materials. Smart materials. Shape memory always. Nanomaterials anyhow like from the 2 days we are talking. So I don't ask that. Any other like new materials? So like why functional graded materials? Let us last in the tomorrow's class. I'll talk about that. Why functional? What is functional? All these things. This one will skip it. Yeah. Have you heard hybrid? Basically, in a plant, we heard about hybrid plants. What is that actually? What is a hybrid plant? Generally, we heard about a hybrid bananas, hybrid something, hybrid fruits or something, hybrid plants. What is that?
Mixing two different species.
So genetic engineering, we can say genetic engineering. That one kind of a species we can take it and then mix with some other species, where we can develop more materials, more terms with a lesser height, all those things. That means combining two different kind of same concept materials and then making a new kind of materials. That we call as hybridization. These particular composites will go for hybridization. That hybridization terms tells you like wherever we have a less strength material, we add it into polymer. For example, let us take give an example of bat threads Fevicol earlier. Still, that threads what we added won't give you that strength to sustain the ball force. When a ball is coming and then we are hitting it, that ball won't sustain for that. So in that case, along with this particular cotton threads, if you use a silk threads, one layer will be a cotton, another layer will be a thread, silk, then the silk having a high strength, high stiffness. So with these two combination, the strength will be enhanced, doubled. So that is called hybridization. In one layer we have another material, the another layer will have a different materials. So two different kind of materials, that called as a hybridization. So here in the simple example you can see it, we combined one bamboo sheet, one glass sheet, one is a natural one, other one is a conventional glass sheet. So we combined two different materials to replace glass. In different fields already we have a glass composites. To replace that particular glass, we used a bamboo sheet. One is a bamboo sheet, another one is a glass sheet. We hybridize the materials and we'll start testing it. So that's called a hybridization, combining different kind of fibers. The another concept is a filler concept, adding a fillers to materials. As I said, like silicon carbide coating on the surface. So probably everybody has seen metals and all those things in terms of rods and other metals. So here metals are available in terms of powders. Aluminum, carbon, magnesium, titanium dioxide, zirconium dioxide, all these we can fix it, add to a composite. In a polymers, in a metals, ceramics, we can add all these things. So coming to the concept of nanocomposites, as exactly like related to our concepts, nanomaterials. So we see nanocomposites. So I think already when they talk about nanomaterials, nanocomposites, nano concepts, have they talk about like how small it is? How much small it is?
Less than
10 to the power of minus 9. How much small it is? 10 to the power of minus 9 is a mathematical term. How small it is?
100,000 times of a human.
1000 times of microns or something. How small that is? Because we need to know, right? Like we are saying mathematically. If I am not a mathematical guy, I don't know 10 to the power of minus 9 means I don't know what is 10 to the power of minus 9. Name some material which is nano. No. Huh? Virus. Okay. Virus is a one material which is a nano level. Okay. Good. Any other? What? Dust particles. Yeah, dust particles may be in the nano level. Any other things? A bacteria. So before going to this one particularly, I'll show a small comparison, which will be interesting to understand it. This one. Because if I start with the bigger one and then go to the slower one, then we can understand. Because even as anything, we will start easily comparing with others, right? He had something, I don't have something, all these things. Like this, I just made a small comparison. You can see it like this is an artist star. These slides are old. Don't say that, sir, now the new star and the chat GPT, I just typed the new star already, the bigger star is there because it's a old PPT. So when I prepared, this one is a VV Chapa is the largest star. I just compared that star with the sun. How many times you can see it? That is 1900 times. That's the biggest star compared to sun. I just compared the sun with the earth. The earth's diameter is 1 to 756. It's not increased, same as same, because the size is not increased, same. So this is 342 times when compared to sun, not with the largest star. And I just, again there are different materials, I don't want to waste time. So I jump to a single child, like a child with 1 meter. So why I take child means then we have some other terms which are related to the child. Okay. So child is 1 meter, this is this much times 127560000 times. And coming to this micro level, a small coin, a penny, that is 2 centimeters. I think you might have seen raindrop. Morning also we have a rain. So you might have seen the raindrops. The raindrop is 1 mm. What is the least size which we can see with our eyes? Probably in the earlier 2 days, no questions, right? Directly they'll talk something and then they go on. Now I'm asking more questions around. Because it's afternoon. If I continuously talk, already you will have a sleep. Then I will get bored if everyone sleeps, right? So what is the least size which we can see with our eyes? Millimeter. A millimeter, like any material, like any name of material, which we can see with our hair. Because already they have last year class. They start in my subject, so they are telling me hair. Here also I have given that hair. So the least size, okay, ठीक है. Then now the thing is how you can see a hair in terms of length or diameter.
Length.
In terms of a diameter, we can't see it. We can see that's the least size. In length, it depends upon the length. If it is a higher length, we can see it. Diameter size, that is 100 microns. That is the least size which we can see with our eyes. Below that we can't see. Okay. So that particular hair, the next one is the red blood cells. As a bulk we are seeing it. Beyond that we don't see. Now we are going to a nanozone. When we go to the nanozone, all different kind of materials which we don't want to study, which we don't want to listen, like bacteria, because it won't be good for our body, we don't talk about it. So bacterial phase is 60 to 70, a flu virus is 100 nanometers. So all these are dangerous things. And some other gold particles is 13 to 50 nanometers. The final thing is a DNA, which a human body will be generated. That DNA is 2 nanometers. I just compared with that DNA, and you can see the arts one, it is 12756 into 12 zeros. That much small. Okay. So to compare that, how much small it is, we need to take a bigger one and then show a smaller one. Any comparison gives you a better understanding. So, for example, if you see in a YouTube or anything, they will make a zoom continuously and then show a small part and then zoom out. Then you understand, okay, that much small. Two options is either we can see it, making a magnified, or else comparing with the higher one. So that to understand it, I just made this one. So this much small is a material in the nano level. And this much small material, again we are making into polymer nanocomposites, metal matrix composites, ceramic matrix composites. When we don't see our hair's diameter properly, then how you handle that particular nanometer? From the last 2 days you have a different classes, right? Have you asked, sir, the nanomaterials you are saying how to hold it? When we don't see it, how to hold that? How many of you heard about nano machines or something? In medical terms, they say always nano machines will be there that cures the cancer cells and then all the things. Nano robots. What is nano robots? As you said, 10 to the power of minus 10. I said like comparison is that much small. Then what is a robot? How we can operate it? How we hold it? 10 to the power of minus 9, which is very small, which we don't see it. Then how to hold it? Because the lectures are going on, you are like listening about all these things, right? Yesterday also just I have a few 1 or 2 minutes he's setting about crystals and then the nano level, all the terms. Then the concept is that crystal we can magnify it in a FSCM or TEM, we are seeing it. Then how to hold it, how to use it, how to add to a composite. Because we are saying we have a polymer nanocomposites, metal nanocomposites, which we can't see, how we prepare that. So the definition says one phase will be in a nano level, the other phase will be in a higher level. The matrix, continuous fibers will be in a higher level, only nanoparticles which we develop adds to it to enhance the properties. So only one phase will be in a nano level, the other two phases will be in a micro level or a higher level. So that is called our nanocomposite. So the one phase which we add to a material says nanocomposites. If it is metals, metal matrix nanocomposites. If it is polymers, polymer matrix nanocomposites. If it is ceramic, ceramic matrix nanocomposites. Coming to this one, I think earlier section about nanomaterials, you have about this nano classification and everything. 0 dimensional, 1 dimensional, 2 dimensional, 3 dimensional. I don't want to talk this about this dimensions, morphology, state, and the composition. All those things. I'm skipping this. So just given like what again this one is a chat GPT. Okay. I didn't give a references of it. Then that's what I'm telling about this. This I taken this. What exactly this in a chat GPT, if I say polymer nanocomposites, how it will be, what representation it will give. This is given like this. So in a polymer, these are the different nanomaterials. We have a 1-dimensional, 2-dimensional, and 3-dimensional, 0-dimensional. 0-dimensional are the particles, 1-dimensional are the nanowires, 2-dimensional are the nanosheets. So they have taken different thing and they combined with this polymers and make a polymer nanocomposites. So polymers are mixed with the different kind of particles and they develop it. Then as what kind of fabrication things can be done, nanocomposites. It shows a solution can be mixed. In the solution we can prepare and melt mixing we can do it, or else polymerization. These three things can be done to develop polymer nanocomposites. Again, as metals, how the metals can be done. So metals, it gives like metals can be mixed with some other metal nanoparticles. This is a metal material, metal matrix, metal nanoparticles, and form a metal nanocomposites. Means, let us take aluminum, copper nanoparticles, add copper nanoparticles to the aluminum and make a new structure like nanocomposites. Whether it may be using a benching like melting method or else powder metallurgy method. So in the powder metallurgy also we can do it, or else directly mixing the melting the materials and adding the particles to it. That's called as stir casting. The stirring will be done and the casting will be done. This is about ceramics. How to make a ceramics. Combining two different materials in a powder blend and centering and then finally making a ceramic composites. So only difference in all the three are adding a nanoparticles to a metal, polymer and ceramics, making a composites. So now the concept is why nanocomposites. Earlier, have you seen what are the advantages of nanomaterials? What exactly the advantages of nanomaterials? In earlier sections you have things like nanomaterials, nano advantages. What are the advantages of nanomaterials? It is very small, which is not visible, so it is advantage. Higher strength, which is not visible, having a higher strength. Good. Next. High surface to volume ratio. Okay, what exactly it is? He's saying like high surface to volume ratio. What exactly it will use?
catalytic reaction. High catalytic reaction.
High catalytic.
More surface area.
More surface area means
More exposure to the more reactable
more exposing to environmental area. Okay, what happens exactly? Fine, the answer is correct. If you have a higher surface, lower particles means higher surface, more exposure to the environment. What happens? But is it advantage, disadvantage?
It depends on
For example, let us take, I have a very big lid, I am working on it, friction will be very high. For each and every bit will be increased, right? As surface area is increasing, that is advantage. Then, what you said is an advantage or disadvantage? Sometimes it's an advantage, sometimes it's a disadvantage. Okay, let us take one example, let us have one book piece. So, let us say, tell me like, what is the area covered by this? This is, let us take, this is a micron particle, okay, more than micron. So, what is the area covered by this book in this room? If you place on a floor, on a table or somewhere, This is a length, width, that is the area covered by the thickness. So what exactly I'll do is nanomaterials means cutting the materials into a lower level. So which technique we can use to cut the material? Any fabrication technique you have studied, right? Yesterday you have ball milling. Have you seen the ball milling? No. Means earlier you have seen, not yet. Okay, ball milling is what exactly we do? We'll put this book in the ball mill and then cut it into small pieces.
Yes, sir. The ball will interact with the conductor. They will interact.
Okay, it interacts with it and then breaks the material.
They collide.
Okay, let us take not a bigger one. We'll take a scissor and then we'll cut it. So we cut the material, we separated this one. Now what is the surface area? It's a double. Not about thickness, it is increased. I cut the one more paper, spread it here. So if I cut all the papers, if I separate entire thing, it contains entire floor. If I assemble everything and make it, it is a small area covered by it. If I start separating it, entire floor will be covered by this book. Okay, so that's what comes to the nanomaterials. When you cut the materials into lower level, as he said, surface area increases. If my objective is to fill the floor in this book, if I place at one location, there is no use. If I cut it into small pieces, it will increase. That's the first advantage, which I want to show it here. Here you can see it. We have taken a small cube to understand it. A cube side is 5 mm, 5 centimeters or 5 centimeters we can take. What will be the surface area? It has 6 sides. One side will be 5 into 5. 5 into 5 into 6. The total surface area is 150. What we have done is, we cut this into 5 horizontally and 5 vertically. Then it become a 1 cube, 1 mm cube, 1 centimeter cube. 1 centimeter cube, each cube, the surface area is 1 into 1 into 6, 6. When I cut 5 horizontally, 5 vertically, then I'll have 125 cubes. That 125 cubes into 6 gives you 750. Means, when a larger particle is there, it occupies certain area. When I cut that into smaller pieces, surface area is increasing 5 times, 10 times, it depends upon the number of cuts. So the surface area is increasing continuously. After that, the next advantage, just we have taken a composite. This is a polymer plate. In a polymer plate, I fixed a particle here. What is this black portion? So this is entire polymer plate. In that we added one particle which circled into the black. What exactly that is? I am holding this particular pointer with 2 my fingers. What exactly between my fingers and this pointer? What is that interaction?
Electromagnetic.
Van der Waals force.
Electromagnetic interaction.
Electromagnetic interaction. Any other thing? The simple thing is there is an interface. I am holding it. Just simple bit. I am just holding it. In a single finger I can't hold it. Okay. 2 fingers I can hold it. Then what is the chance? There is a chance of falling of this material very high. 3 fingers, interface increases. 4 fingers, more interface. 5 fingers, more interface. If I hold like this, better holding. So what exactly is happening is the contact point between my fingers and the pointer is increasing, interface is increasing. Okay. So this is called an interface. This black region is an interface between the polymer and the particle. What exactly we have done is, again we put this particle in a ball mill, cut into small pieces, we cut and then distributed inside the plate. So same particle, the area what approximately we covered is of 6%, the interface is 4%, the black region. So we cut into small pieces and then distributed here. The total area remains same because we are not adding a new material. Only what we are doing is we are cutting it into small pieces. So the area remains same. The black portion which covers this particular area is increased to 45 times. It's an approximation. It's not exactly like we did measured it. Approximation 45% means the interface area is increasing with this one. So one advantage is surface area. The second one is when you go to nanomaterials interface. The third one is how many of you studied about crack propagation or understand about crack propagation? Have you heard the crack, right? What exactly that physics people, I think different people are there. Just like you have crack, for example, to understand it simple, I think these are some kind of a wood and different kind of thing. If you see a normal wall, outside of this wall, when you have a break, we can see a wall, on the top of a wall, there is a big crack. Means breaking of a wall, like you have a crack on the surface. Once a crack is formed, in which direction it will propagate? In which direction it will pass? Where there is a weaker section, weaker material, in that direction it will pass. So, in the particular weaker section, if you have a new material which are stronger, then it won't pass. It will resist some time. So here you can see it. If a crack is started here, comes here up to here, it breaks the interface and passes through the entire material, break it easily. So the life of the material is very less. The same condition, if it is initiated here, every time to pass to this end, we have 5 to 6 obstacles. Every time it has to stop, take a new direction or pass through it. So to break that entire structure, there will be a 6 obstacles here, 6 to 7 obstacles. Here we have only one obstacle. Once it breaks that obstacle, the entire material will fracture. If in this condition we have a 6 to 7 different materials which stops continuously the crack. So that's why the life of the material will increase. So as I said in the first starting example, the ancient time, the bricks, they use 9 to 10 different kind of materials. They used animal waste, bones, eggshells, sand, different kinds of sands, different particle sizes of sands, rice straws, all those things, 9 to 10 different materials they used it. Each different material have a different properties. When they combine all the materials act as a single material. To break that material, if any crack or anything comes, they have to break all these properties. So that's why the life of that particular bricks are very high, thousands of years, still it is intact. Whatever right now bricks what we have, it's a consist of only 2 or 3 materials, like one kind of 2 3 kind of materials, 2 3 different kinds of a sand. So once it have a resistance to break that, it will break that. That's why we'll have a 50 years or 100 years life. So the crack propagation is another advantage with this particular nanomaterials. So let me have a break or continue this. Continue. If it is okay, then we'll continue. Like otherwise, we'll take a break. What's the time? 3:20. The mandala is done. So if you want a break, 10 minutes, we'll go for a break, and then we'll continue one more. Is it fine? Just please check it once if we have. Nano composites and composites. But the schedule is slightly changed, so we are planning it tomorrow. So I'll have a 2 hours lecture, and then the professor will come, and then he has a tutorial one lecture today. So in this particular thing, today I'll explain how to fabricate a composite, and tomorrow we'll fabricate that. 1 or 2 composites. My students will help you, like they'll fabricate few samples, and you can see it. You can see the fabrication techniques and what basic techniques, what things we'll adopt. Like we started this particular fabrication. Earlier there are the different kind of concepts we have. There are filament binding, bulk fusion technique, vacuum bagging technique. There are different techniques to fabricate it. So we need to adopt a basic technique where we can fabricate a material easily. Okay. So the traditional technique is a hand lay technique. In the name itself, like a hand lay up, means using our hands we lay the material and then fabricate it. That's what is our name called a hand lay technique. Okay. So what we prepare is we prepare a mold. Once we prepare a mold, then we go for calculations. We calculate it because we need to fabricate a plate. If I want to fabricate a plate, then we need total volume of the plate. I need to calculate total volume of the plate. In the total volume of composite, we are adding 2 terms. One is matrix, another one is a reinforcement. So the equation gives you like volume of composite equals to volume of matrix plus volume of reinforcement. So the total volume of a composite consists of a matrix as well as reinforcement. Two terms will be there. So in these two terms, how much amount of matrix to be added, how much amount of reinforcements to be added, that comes a designing part of a material. So always we need to design our own materials. For example, if I want to design a material which having a higher strength, then I'll select a higher reinforcements. If I want to design a material with a minimum strength, but I need a basic full protection of a matrix, then I go for a higher matrix. Okay. So coming to this, before that, I'll ask you one more question. For example, if I want to make a sugar juice, how much sugar spoons we will add it in a 1 liter of water? Again, it depends upon the person to person varies. Assuming that we'll add a 1 or 2 spoons or 3 spoons of sugar. If I add a half kg of sugar, in 1 liter of water, then what happens? Sugar juice will form or not?
No.
No. Why it won't form?
Saturation.
Saturation will be done. Means, are we adding a water to sugar or sugar to water? A sugar to water. In a sugar we are adding a water. Again it forms something. Let us assume 1 kg of sugar, 1 liter of water. Sugar remains like a crystals. Water is added to it. Water will be absorbed and then crystals will be visible. Half kg still, but mixed with the water, some kind of waterish kind of thing will be. Then what best combination will get? In a 1 liter of water, add a 3 spoons of sugar, it's perfect. More sugar means not possible. Saturation is coming. So in the designing of matrix and the reinforcement, there may be a saturation point. That saturation point gives you how much amount of matrix to be added, how much amount of reinforcements to be added. So in that particular thing, for example, if I am making not a sugar juice, lemon sugar juice. Okay, lemon sugar juice. Then how much of lemon we'll add? Lemon is a water, right? We can add 4 or 5 lemons. What happens? If I add 4 or 5 lemons, make a this thing and add to the water, can we drink? We can't drink. What happens? It will be a more like citric kind of thing, right? So which we can't take, because if we add more material which is having the same properties, that also we can't take. Here the liquid sugar saturation is there. The other material which is in a liquid state, if we add more also we are not taking it. The same concept applicable in the designing of composites. Whenever we are selecting a material, reinforcement will select. In that matrix we are going to add, that matrix will be very high as like water. The sugar which we are going to add 2-3 spoons, that remains like a reinforcement. Reinforcement gives you strength. We can add 60-70% of a reinforcement and then 30% of a matrix, which won't wet the material, because that much high amount of reinforcements never wet or make a structure with the lower amount of matrix. So when we are designing it, we need to see matrix will be higher, reinforcements to be lower. Hybridization means the new material which we said, that will be a limited level. So when we talk about later comes to the composites, nano composites, I'll tell that what combinations, what things right now research are going on, and what we are trying, what we are doing, that I'll explain. So this is hand lab technique. So as we are preparing a sugar juice, these composites are similar, because many people say like when we are doing a research, always there is a point like you are doing like a research like making a juice. Means one material modified with another material, either banana juice, pineapple juice, juice will vary, right? Composite also similar like that. In epoxy matrix, put Al2O3, Al2O3 epoxy composites. Put the same thing instead of Al2O3 SiC composites. Combine Al2O3 SiC, SiC3 Al2O3 composites. So it's like a juice. You add new material, new juice will come. But the thing is whether it is having an application or not, whether what kind of material it is, that comes after once you prepare the material. Okay? Let us talk later, come to that. This is a hand lathe technique. The same thing. The another technique is a filament binding. This particular filament binding, you can see like how many of you heard about Indian missiles? Have you heard about any Indian missiles? What kind of rockets, missiles we have for fighting with other countries? Agni, BrahMos. Okay. If it is Agni, BrahMos, like for example, Agni 1, how much distance it will travel? We know Agni's, BrahMos, how much distance it will travel, that we don't know. It will be very big, right? Not a small one. It's a very big one. Okay. That is at least you know that. Then you tell me like how much distance it will travel. Agni 1 travels 500 kilometers hardly. Then if I want to fight, I don't name a country which will controversy like okay, any country something XYZ. Okay? So I want to put a bomb on XYZ country. So if I put from Hyderabad, from DRDO office, then where it will fall? 500 kilometers means it will go on far on Nagpur. Correct? It's a 500 kilometers in Nagpur, right? From Hyderabad. So if I put it here, it will fall on Nagpur. If I want to put that same thing to some other country means I'll go to border, I'll take all the things and then put that missile from the border. I'll develop in Hyderabad, transport it to the border. From the border I'll put that missile. Okay? That is for Agni 1. What exactly in the Agni 1 happens is, the entire Agni 1 is cased with metals. The entire material is developed with the materials, with the metal materials. Agni 2, 1000 kilometers. Agni 3, Agni 4, now it is around 3000, 5000 kilometers. It's an intercontinental missile. So means sitting in Hyderabad, we can switch on and then we'll hit some other continent. Okay? So that's the point. Like nowadays, these concepts what we have, if you see the US and other countries, they have almost 30-40 years back. Okay? That's why we purchase everything from there. Nowadays, we are studying about composites. Many are seriously listening about composites. I started 15 years back. We are now studying it. Okay? After 15 years also we will study this. But the other countries, they start studying about it. Because they are recycled it already. When I started, they are in the recycle stage. All the US, Europe, Israel, all those, they are recycling the composites. Means develop, used, recycle. We are in the developing stage. Now they are developing functional graded materials. So in the class, 90% of the people don't know about functional graded materials. They are developing it. So we will develop that after 10 years. Okay. So start learning the new things. Why I always say like in a classes means, but sir, what you are doing, like why don't you develop? So we are developing it, but it depends upon the people, right? If people don't know, if I say FGM, if they don't know about the word, then I always say something which is not going to our minds. So first people has to know about the new materials, new concepts, new technologies. Always exactly what the research is going on. Some X material prepared one kind of a juice. I'll change the fruit, make a new juice. Or else I'll combine the two fruits, make a hybrid juice. This is what going on the research. Okay. Still I'm also doing the same thing, I'm not pointing to someone else. But the limitations we are doing it, if we know the new things, new materials, new concepts, then we can develop new things. Only thing is if you don't know the terms, don't try it. First at least knowing the terms is first important. If you know the terms, so then we'll start thinking about it. Okay. So my topic is about like not exactly about nanomaterials and not about the concept. My concept is about like at least know new materials. Somebody asks, okay, gee, I know that. I know this material. For example, almost 2 months or like 1 year back, I don't know ChatGPT. When you're telling that, then I feel like I don't know about ChatGPT. Now I learned ChatGPT, I'm imaging, develops, and all those things I'm doing it. Okay. Still, many people don't know about it. And DeepSeek and other terms, new terms are coming, right? So we need to upgrade ourselves. If we don't upgrade ourselves, then we are out. Okay. So nowadays many things are going up, right? We need to upgrade. Like materials, every day we need to upgrade ourselves. New materials are going to come. If you don't upgrade yourself, if you are stick with the same old materials, it won't work. So this is a filament binding in Agni. I'll start there like Agni missiles. They use this particular filament binding technique. To develop all the DRDO labs, they use the filament winding technique to develop a composite casings. All the composite casings they develop with this, and then it will be a carbon fibers. So the casings they develop, 3 motors will be there, 3 casings, 1, 2, 3, because the fuel will be very less to transport a 5,000 kilometers in a small tank. You don't fill the continuously, like for example, missile is going, we'll send a one more filling missile in the back, it will fill the fuel, it won't like that, right? Once it starts, go, that's it. So there will be a 3 casings. So one casing will comes at some location, after another casing, finally bomb will go and fall on the 5,000 kilometers. So that's what the concept in the missiles. So they use this particular technique. The filament winding is an old one, old image, and vacuum bagging technique. Now the question is, yes, we have seen different techniques, right? 3 different techniques we have seen. There are more techniques. What is the need of, like, once we have one technique, one manufacturing technique, probably I think if it's a nanomaterials, if I say, you might have seen yesterday some manufacturing technique, soldier method, right? We have seen soldier method. Again, that is modified to some other technique. Once we have the ball milling method, why need our soldier method? Once we have a soldier method, why auto combustion or soldier kind of advanced methods? So what is the need of it actually? Why we are going for a higher techniques? So every manufacturing technique have certain disadvantage. Won't gives you a better material. When you fabricate a nanomaterial, nano composite or a composite, any kind of a fabrications, there will be certain defects in the fabrication techniques. To address that, we modify the technique. In the very first one I said, this one we'll do in a normal atmosphere. In a normal atmosphere we're doing it. Then what happens exactly? We are mixing the material in a normal atmosphere, combining 2 materials, bubbles will be formed. That bubbles, if you keep it in an atmosphere for a longer time also, it won't come out, because the bubble formation will be very high, won't come out. If I directly pour into a mold, then it will saturate and it will fix inside it. It forms a voids. When there is a voids, at the fabrication stage itself, I have a defects. Then when there is a defects, then there is no point like we have a better material. So to avoid that, we go for a vacuum, keeping that entire in the vacuum bag to remove that bubbles, air bubbles. That's the vacuum bagging technique, filament winding technique, pultrusion technique, hand layer technique, spray up technique. So there are further techniques are modified with these things. Okay. So with these terms, like before going to nano fabrications, I think already you have seen it. So we'll have a small break. There are different terms. I don't want again go to this because earlier professor already talked about it. Just for only 2 techniques what I developed when I'm doing my PhD. I'll just talk about that. So one is a ball milling. When I done my PhD in 2011, so I used that. So I just talk about that particular terms, that ball milling and then auto combustion process, where we can develop alumina Al2O3 with a low cost, we can say, low size materials. We can fabricate on a lab. What I have done in my PhD, that I'll talk for 15 to 20 minutes. That's the next one. And these other terms are like top-down approach, bottom approach. I think already discussed, right? Earlier classes, I think already done. What is the top-down, bottom-up approach? All this. That's the process. So this process I'll discuss. These 2 things. After that, we'll talk about characterizations. So how to characterize it. So what are the steps involved in it? How to understand the material? Because as of we have just seen the composites, nano composites, different materials. To understand in the next level, we need to characterize it. So after a break, we'll see those things. Okay. So quickly, like right now it's 3:40. So we'll have a break for 10 minutes. So up to 3:40, 3:50 we'll have a break and we'll assemble by 3:50. We'll start the break. Yeah. Thank you. welcome back. So before this, we have seen some publications related to nanomaterials, nanocomposites, and composites. Now, just characterization about the materials, characterization of composites, nanocomposites. So to understand any kind of a material, first we need to characterize it. We need to understand test the material and then see the properties. Once we see the properties, then we understand the material in a better way. So coming to characterizations, mechanically we have tensile and compression. Tensile means apply the load of opposite side. If you pull the material, so in opposite direction, so how the elongations will happen. If it is having a continuous fiber, discontinuous fiber, random fiber, different kind of fibers or particles, how it will stretch, how it will fracture. So all those things will come study in the tensile test. Next one is the compression. Compression will be in opposite direction. We'll compress that. Once we are compressing it, then how the load is observing, and after that, once the load is observed, and finally how the fracture happens. Those two things will come under compression. Normally in a tension, when you are applying a load, the fibers will stretch. When you talk about, as topic is about nano, so I talk the level in terms of a micro level and nano level studies. When we study any kind of a material or a subject or any concept, there is macro studies, micro studies, nano studies. Macro studies means outer level, like just see the material, fracture it, break it, see that how it is breaking, whether brittle or ductile. Micro level means understanding the deformations, how the material is elongating, how the material is stretching, and finally how the fracture is happening. Coming to the nano level, it about the atoms, how atoms are dislocating, how atoms are moving, how atoms are stretching. So in this particular thing, so we have a plastic deformation and elastic deformation. Any material, whether it is a ductile or a brittle material, so we have an elastic deformation and plastic deformation. Basically in a brittle materials we don't see any plastic deformation. Means more elongation with the load. We have a failure at one point, a maximum amount of load is observed, fracture at one point. That is what we see in the brittle materials. When it comes to the ductile materials, there is a more elongation. After elongation, the length will be increased, finally fracture will happen. That's what exactly in this we have a different kind of lines. Elastic point, yield point, ultimate point, final fracture point. So for a ductile materials. For a brittle materials, we have a single point, slightly fracture will happen. So always I'll ask a question, whether in a brittle materials, do we have a plasticity? Sorry, do we have a elasticity? In a brittle materials, is there any elasticity inside it? For example, if I apply a load for a brittle or a ductile material, well below the yield elastic point, means just the capacity is 100 kg, I applied 5 kg. I applied a 5 kg load, removed it. Whether it may be a elastic material, the brittle materials or a ductile materials, both is in the elastic zone only. There is no change in materials, no change shape or anything. 5 kg means in the both materials showing elasticity. Only thing is that deformations not visible in brittle materials. Deformation you can't see it. In brittle materials also there is elastic point. That deformation we won't see it because that material suddenly fractures to the maximum point. These kind of elongations you don't have. That's why you don't have a plastic point and then all other points. Finally, we will have a fracture point in the brittle materials. So, how this particular in terms of atoms, if you see the image, in this what we have done is, we have taken a material, we have taken a small slot to study that. This is the slot what we have taken. We assume we have 20 atoms, like for example these are 5 outside, 5 into 4, 20 atoms we have taken, and then we apply the load. Once we apply a load, we apply it well in the elastic deformation. Means the load is within the elastic deformation. What exactly the atoms are happening is, these atoms, of line of atoms, you can see a gap here between these two, this one and this one. Means bond stretching will be done. Between the bonds there is a bonds are joining between the atoms, right? That bonds will stretch within the elastic point, and after that the length is increased here. You can see this one, the length is increased, means bottom atoms are stretched with their bonds. After that load is removed. This entire load is removed. Again it comes back to the same structure. That's what actually we studied, like elastic limit. Within the elastic limit, when a load is removed, that comes to original structure. Means all the atoms will stretch and then comes to original structure. That is what happened in the elastic point. When it comes to plastic zone, what we have done is, we applied a load to the maximum extent where it changes the permanent shape of it. Means it crosses the elastic point. So here elastic plus plastic zone. What happened here, you can see it, these atoms in a line we have 4 atoms. In the total we have almost 20 atoms. When a load is applied to the maximum of beyond the elastic point, all the atoms stretching is also done. One set of atoms are slipped to the lower level. Means length is increasing. As we have tested in the tensile test, always we will say the length is continuously increasing for a ductile materials. We are not adding a new material. The side we are not adding a substitute material where it can increase the length. It has to be taken somewhere else to increase their lengths. When it is taking that, particularly whether it may be a thickness or a width, that will be reduced, length will be increased. So in that condition, you can see these particular atoms, the 4 atoms, one atom is slipping to the lower level, the other 2 atoms are slipping to the lower level. Continuously that happens in all the things, and finally we have extra atoms which permanently increases the length. There is a bond stretching as well as atoms slipping to the lower level. After that we release the load. Whatever the bond stretching which is happened between the atoms within the elastic zone, that regains its original structure. So these atoms, between these 2 atoms, whatever the length is stretched, it comes to original structure. If you draw a line here in this point, you can see how much variation it happens before elastic point and after elastic point. How much amount of load it has taken, how much amount of elongation it has happened before and after. So this gives you a clear analysis to understand how the loading conditions happens on a material. So if you draw particular that kind of analysis, that will be a new thing, because everybody talks about only what is the highest and lowest. If you start saying that how your material after deformation behaving, before deformation it is happening, before deformation how it is acting, after deformation how it is acting, that particular terms gives you a clear analysis to write a better journal, a better analysis in the calculations. Next one, this is already have seen it. The next point is fracture happens, material fractured, break. After that we have a curve, a beautiful curve in the system. We'll take it and then we'll put it in the paper, and then we'll start analyzing that particular values. Majority of the terms, for example, if somebody asks do some kind of a microstructural analysis or some analysis, then only we'll see the image, what happens to the material. Majority of the times what we do is we'll send the sample to some lab, they will break it, they will give us a graph, we have value, that's it. We never see what happens to the sample, whether that sample, how the fracture happens, whether a cup cone structure is formed for a material, or if it is a polymer or some other material, how the end portions fractured, whether it is a continuous or crossed, or in which direction fracture happens, which place fracture happens, all those things we don't bother. If you start analyzing those things, then it will give a new break to understand the material in a next level. So you can see it, this is a cup cone structure is formed. So one side we have a cup, other side we have a cone. 2 halves are formed, and necking will be done, and then finally fracture happens in a ductile materials. If you start studying again, everybody, like for example, it's a time like what we can say, like we can have all constraints, equipment constraints, money constraints, all those things. If even somebody asks in a journal or some other things, we always see, we'll take one sample, we'll take 4 or 5 images, we'll show that. other end of the sample, we don't take it. When a fracture or a break happens, we need to analyze the two halves of the material. This half and that half, because when you join these two, that is single sample, when it breaks, in the two halves, other sides what happens? This side what happens, that side what happens? For a curve, what is a failure? For a cone, how it is formed? Why in this side only cone formed? Why not in this side? That is which side, whether in the top side or lower side? Cup forming or cone forming, in which direction it is forming, and how much amount of deformation is happening here, and where the fracture starts and where the fracture ends. So all these kind of analysis in a single tensile strength gives you a better PhD, a better output for an understanding. So in this particular thing, to understand it whether it's a ductile or a brittle, basically some studies related to that. One is necking will be done. A necking will be done, necking will be started. In that particular necking, once the material already stands, like I said, atoms deforms. Atoms will move from one location to another location. When it already crosses the plastic zone, when it enters in the plastic zone, atoms slips to the lower levels. When atoms are slipping, then these kind of cavitations will form. Means atoms are moving from one location to another location. That atom gap called as a cavitation. Cavity formation will be done. Once a few cavities are formed in the material, that cavities will join together and form this kind of crack. Means 4 or 5 cavities are formed together and then adjacent cavities join together and finally form a crack. After the crack, continuously we are applying the load. The material lost their ability to strain more. Stress, don't take the stress more. So it's straining continuously. Then the crack propagation will take place. The crack will propagate and finally a fracture will happen. If it is a ductile, we'll see all these kind of behavior. Cavity formations and then crack formation, crack growth, and finally crack breaks into two halves. The material breaks into two halves. This finally analysis we can see it. But if it is a brittle materials, we don't see that. In the brittle materials, directly it will absorb the maximum amount of load. Finally, fracture will happen. But we can see that. You can see that one. This is a brittle failure. There is no deformation and it's a compression load. So you can see that directly once a load is applied, directly a cracks will develop on one point and then fracture will happen. So in this particular ductile materials, we have all these mechanisms like we have cavity formation, cavity growth, and finally crack formation, crack growth, and finally fracture will happen and become a two halves. If you study this particularly compound structure, in which direction cup is forming and which direction cone is forming, and that analysis gives you an idea in how the material is behaving. And for a brittle material, we always see that particular surface on one end. We need to see the other end how it happens. Other end also how the breakage will happen, whether it is a crack formed or how the crack is propagated or stopped. When it comes to composites, we have a combination of two or more materials. Which material is propagating the crack? Which material is restricting the crack? So what is the material? Like which material is an advantage, disadvantage? That entire studies also will come here. If it is a composite, if it is a single material, then how the failure is happening, how the load distribution is happening in that material. That entire studies will come here. This other thing like as I said, tension, compression, torsion, flexural, and shear. So these entire tests. Tensile test will do it in a UTM, Universal Testing Machine. So tensile, compression, flexural, all these we do in a Universal Testing Machine. So this one to illustrate like the surface cross section area and how the elongation will done, how the curves will come. Some animated videos like you can see the tensile test means applying the load and then specimens are elongating. So necking will be done before that. And you can see this the polymer testing. Load is applying continuously, the length is increasing. You can see the curve is forming here due to stress and strain. And this is a cross section area, whether rectangular or circular, or the cross section. This is a dark bone shape of a specimen. How we prepare? Why we prepare a dark bone shape for testing it is, I think probably load, like we can say like load stress concentration point. So the stress concentration point, if it is a uniform specimen, so we can't predict where the stress is happening. So we need to create a specimen such a way that load transformation and a stress concentration to be applied at one point. If we make this surface with the different dimensions, where we have a lesser diameter, that will be the stress concentration point. There the entire load will be applied. In this particular gauge length, the load will be applied and the fracture will happen in this particular area only. You can see it here also. When it is elongated in the center, the failure will happen. This is like if you apply a strain gauges. So how this particular material slowly stretches when you are applying a strain, how much amount of stress is applying and how strain is happening, at which point it breaks the elasticity and it goes to the elastic limit and finally goes to the maximum ultimate point. So when you apply this particular strain gauges, we can see all these points. And there are general mistakes when we are doing some kind of a characterizations. Always when you test a tensile specimen test, 100% we never get same kind of a result. We never get same kind of result two times because we'll have a material defects, manufacturing defects and testing defects. Majority of the times we'll have a testing defects because when we are fixing the sample, sometimes we'll fix it correctly, sometimes we'll fix it in a different alignments, sometimes different angles. So these things, if you don't care, if you don't see about that when you are fixing that, then there will be a more chance of getting wrong kind of results. So these alignments are wrong, then automatically the material failure will be different level. Here I just given an example like for a ductile materials and a composite. The composite having a fibers and this is a ductile material. When a misalignment is happened, then due to the misalignment, the entire force is applying here. Because due to misalignment, this entire load, more amount of load is applying in this corner. So on that corner, stretching is happening. In this corner, compression is happening. So the objective of the characterization is to apply a tensile load. But on the specimen, due to the misalignment, what exactly happening is, one end is undergoing stretching, like tension is happening. The other side, this end is going for a compression. So other side is compressing, one end is undergoing tension. So the finally fracture happens, you don't get a clear result, correct value for that. Because the same specimen itself acting, one end is a tension, another end is a compression. So that what happens in the bending. Later I will come to the bending part, where we have a bending forces. There we have the top force, where we are bending it, it undergoes compression. In the bottom portion, it undergoes tension. In a single specimen, we will have a multiple kind of a behavior. So similar thing it is happening here, where one side it is going for a tension, other side compression. Due to that, the failure happens. The same thing if you see for the fibers, the same kind of a behavior, but you can see the curves here. In this we have a different points, elongation and all those things for a ductile material. For a composite, we have a fibers. When a fiber is fractured, whether it may be this side or compression side or tension side, the other entire materials will fracture at a single point. So that's why like the curve is straight and then fracture happens. These entire materials will fracture at one point. So there are many factors which affects the tensile strength. So why particularly among all the characterizations, why have given more stress on the tensile links? As I said, if you want to do a good thesis or good work, only on tensile, with only single tensile test. So these entire parameters if you consider, if you develop a new material, testing all these, considering all these parameters, gives you a bigger analysis. Varying all the parameters, varying the effects of all the materials, and considering all these factor influences, orientation, morphology, and then surface conditions, and the speed, the loading conditions. So all those parameters, if you do the test, then automatically we can characterize the material in a better level. So these few samples what we tested, so one is a Kevlar, one is carbon, and then another one is a glass. So you can see it, all the samples are fractured in the corner level. Our objective is to break this material in the center, but it happens in the lower level. It's not exactly in the center. Means when your tension load is applied, we assume that uniform load is distributed in the materials in the two halves and fracture has to be done in the center. But always we'll see either fracture in the lower corner or the top corner. Then when the fracture is in that corner, we never get an exact correct result for the specimen. Because here there is a void or a very defect which is increasing the stress concentration before sending to the center portion. The load has to be sent to the center portion, and then in the center, when we combine the top load and the bottom load, in the elongation will happen in the center, fracture will happen in the center. But due to voids or defects, this particular fractures always happens here or in the corner portions where we have a fixtures, where we hold the materials. So this is a compression. Already I have shown this. This is a 3-point and 4-point bending test. For any specimen, any material, if you develop, there will be a 3-point bending test and 4-point bending test. Bending will be done using a 3 points, or bending will be done with a 4 points. So when we go for a bending, then we'll have a shear force and a bending moments. So basically in the mechanical, what we see more on like shear force, how shear force will affect on it, and then how the bending will be happening, and what is the bending load, finally the material sustains. So all those things we'll study. What happens if you have a 3-point and you have a 4-point, the load distributions, how it happens, all those things will be there. So this is a small illustration like how to see the 3-point and then 4-point in bending tests. These terms generally in mechanical we'll see more about it, like changing the loading conditions and then uniform distribute load and a point distribution load and then other loads. We'll study all those things. Every time when we are bending it, we assume that there won't be a shearing of layers. Means when we are bending and breaking it, we assume that there won't be a shearing of layers. There will be a shearing of layers when we are bending it. There is a bending load as well as shear load. That shear will be negligible when we have a more bending. So when we bend more, shearing will be less. When the bending is not there, then we go for a shear. Bending won't be there means the length of the material to be reduced so that there won't be a bending load. Shearing will be pure shearing will be done. Their bending will be negligible. That's called as interlaminar shear strength. So the dimensions will be less for that particular characterizations. So tomorrow, I'll continue these characterizations. We have some kind of calculations related to the densities, how the density will be done. Generally, in a density, what exactly we do is we use formula. Density equals to mass by volume. We always calculate by using that formula. Then, but we don't get a real density for it. If we use a mass by volume formula, then if it is a bulk density, it continuously varies. When you compress more, density will vary. So we use Archimedes principle to make it a true density. So what is the true density of a composite? What is the bulk density of a composite? What is the theoretical density of it? And how to calculate the void content. So the void content always reflects the properties of the materials. So that part in the next class, next lecture, I'll explain about that particular terms which are related to densities, void contents, and then some structural properties, XRD, FTS, and which are related to nanomaterials, nanocomposites, and some characterizations related to nanocomposites. If you have a multiple kind of fibers and fillers, so how these interfaces will affect on it, how the research will affect if you have a multiple fillers, fibers, as well as nanoparticles. So when you combine all this, how the interfaces will increase, and due to that, how the material properties will vary. Those concepts in the next lecture I'll talk about it. So now I'll start the lecture with this. Our professor now will take over like the tutorial for the next 1 hour.
Stress, elongation, or compression in nanometer scale. And I will show you how in modern material science we can improve some
material properties, especially thin films. And we also consider some kind of materials, because at the first stage we will focus on materials which belong to class perovskite materials. And it is also summary of previous lecture. We can tune material properties by varying the composition and structure of complex components. It is easy to understand. The improving technology, the reduced dimensionality. When we pass 100 nanometers, we go to nanotechnology, when properties of materials are different than in nature, by preparation and composition materials. And from such point of view, we discuss very in detail why composition and structure of materials. We less speaking about technology, but it's for professional subject when mechanical we working in steel, metal, and another materials in macro scale. It is technology is very important. For example, the same kind of steel when we adopt, for example, in different technology, we obtain different properties. And it is three crucial points if we consider improving material properties. It's a composition, structure, which a stronger influence on materials constant, and in finally for the materials properties. Here is a well-known example. We have some polymorphic structure of materials, because such materials were constructed from the same elements into one element second. It is amazing that such materials possess values or properties like, for example, hardness, like stability, like temperature, resistance, etc., etc. But in our example, material is the same, but structure is different, and it is stronger influence of materials properties. And it's a very interesting example because it is easy, but between carbon powder and diamond is quite different properties. And next example, it is easy to see. We such a methodology applied in the previous lecture. It is tuning properties by utilizing range of composition. Here, I focus on special glass material. These materials which preliminary should be designated for radiation dosimetry. Because one of method of conservation of food in vacuum is kill all bacteria. And we can use by utilizing some kind of source of radiation, from nuclear radiation, UV radiation, and another. But important is therefore needed to measurement of dose of radiation which was applied here. Such materials are called dosimetry materials. And here, value of those we able to evaluate utilizing so-called thermally stimulated luminescence. When we, after radiation samples for 4 days, and we be slowly heating, they start radiation. As such, dependence of signal intensity in function of temperature is well known as a glow curve. And here, analyzing or measure when we measure perform measurements of area under each curve, we can evaluate dose of materials. And here was very interesting relation because dose was possess linear dependence between peak during annealing and value of dose. And for example, when we calculate that it was 17 and a half, it was a dozen 2 kilograms. It is interesting that we can modify materials to obtain simple dosimeter, simple and cheaper dosimeter, which is also environmentally friendly. And next example of my work, it was optimizing glass composition focused on obtaining a strong luminescence. And why we do it? We changing one element, it is a galvanum oxide, but keep unchanging, for example, luminescent sun. And when I was one time participating in a conference in India, I participated in lecture of some medical doctors. And they told that was a doctor from cancer, from skin dermatology, and another subject. And they speaking about some laser therapy and some therapies for skin disease, which is not unpleasant illness. It is looking badly and people feel not comfortable in such situation. It is not strange, it is not influence of life, but it is not bad. And from medical experience was evaluate that 311 nanometers is excellent radiation for activation of skin to back to natural color. And we performed some experiments. It was surprise for us that for a particular concentration of gadolinium, we obtain a very strong signal which was located at 311 nanometers. It was amazing that in such a simple way it's possible to find a good solution, which a good material which can be used in medical equipment. But science is sometimes give unexpected results. For example, we perform some measurements, some samples with intentional change composition. And we predict that when we increase, for example, concentration of substances A, B decreasing, we still will improve materials properties. Sometimes these results are not easy to predict, and sometimes give not unexpected results. Here we investigate photoconductivity in such materials because we were interested to find material for detector of radiation. And it was surprising that it was not monolithical changes of signal intensity, even when we substitute in order particular ions in the position tin, silica, gallium, tin, it was without any sense, and also in a situation when we, for example, in critical position, we obtain different behavior like into fixed elements. But it is a science, and maybe when we put focus on such materials and investigate, it will be very difficult to explain why the such situation is. Next, you know the phenomenon superconductivity. Superconductivity was discovered 125 years ago. When in some laboratories, scientists obtain liquid gases. Because in the end of 19th century, start of 20th century, one of important topics was obtaining a low temperature. And people perform many measurements utilizing such new opportunity. And one of first was very easy, also performing measurements of resistivity as a function of temperature. And was surprised that some materials in particular temperature, so-called critical temperature, resistivity sudden. And it also was very strange because not a good conductor pass such transition to superconductivity state, but materials which in higher temperature were a bad conductors. And for possible application, when we are able to discover such phenomena in room temperature, it will be very useful phenomena, and the materials will be probably very expensive to a possible application. And for example, such materials we can use for transforming electricity. I told you that between 10 and 15% of electrical power changing in wireless onto heat, because it is resistive. But there were many attempts, heavy work. It was difficult to find materials which will be superconducting in room temperature. When I was in your age, highest temperature was a few Kelvin above 20. It was, from a practical point of view, it was impossible to wide application for something possible. Somebody of you working in low temperature, perform some measurements in low temperature, you're using maybe liquid nitrogen or another. No. Okay. Because next phenomena, which was discovered because it is so-called Josephson effect. Situation was as follows. There was Professor Barnum, John Barnum. He obtained Nobel Prize for discovery some kind of transistor. He started working in a different subject. He will have a strong team and working in theoretical foundation of superconductivity. It was interesting that he liked give very interesting topics for PhD thesis or for exercise for students. And asked one student to calculate behavior of special kind of junction. It was a superconductor, very thin barrier, and next superconductor. How practically is possible? Well, you can take a metal which is a superconductor, oxide made oxidation. Oxide is mostly isolator or semiconductor, and we obtain a Josephson junction. And he made job. Professor looked for results and thought it is a very good result. Please send to journal. He sent to journal, article was published, and next people thought interpretation of phenomena is good, but inside in job in article is a many mistake. But it was also important when Professor Bardin was included to acknowledgement. Any reviewer thought probably I not understand well. We pass it. But Josephson obtained Nobel Prize for such discovery, because such discovery is utilized for as a tool for measurement very weak magnetic field. We can perform measurements by flux, quantum of magnetic field. It's amazing why we can able to apply such phenomena. For a long time, it was easy to obtain funds for doing science in such subject because it was a many medical theories, but tissue, which is ill cancer, give different magnetic field. And it was maybe possible to monitoring human body to find a possibility of cancer. And here you can find a model of such equipment. And flux of magnetic field generate so-called Josephson current, and we can see perform and can measurement perform measurement of magnetic field with extremely high precision. It is very interesting, and because it is a tutorial, and I would like to come back to you some stories, some from my point of view, important science which I participate. And now start history. By the way, in last June, I was in my Caustic University when I was a graduate master of physics to participate in ceremony of 110 adversary of born of my professor. He not really I live, but my professor born 110 years, now 111. Next situation with theory of relativity. In such time he was younger than I, and we speaking about him, we have a lecture with grandfather. And he was a person which changed topic of interest, but only one topic not will be the same, carbon. He working with samples with carbon. And when I was pupil in secondary school, he published such a famous article regarding possible superconductivity at room temperature. And from such, it was in ordinary newspaper, information, non-scientific journal, in the daily newspaper, there was information about it. And I think I must be his student in future. And I do it. What I did, he prepared some samples. Later it was 40 samples per every 3 days, which was done very easy. I told you what is the procedure. Probably each of you may do it in laboratory. It was a piece of porcelain or glass, and was put by evaporation electron. Here was a drop of 4,4 alcohol and after temperature, start the process of polymerization. We put such drop to furnace for 100 up to 100 centigrade, and next was put next electron. And it was a sample for performing measurements. And it was a surprise that at DC measurements, suddenly start so-called superconductivity scale, because immediately decrease resistivity below below possible of measurement, because we were using very good equipment. It was not able to perform measurement, but we tried to make some experiments. Some experiments which was performing dependence of current as a function of magnetic field, and after absorption of microwave. And it was when I was a student of second course at physics, a start era of electronic calculators. Before we were using different kind of cube. You're able to see how work changed. And it was a surprise for me when I calculate from such steps, a so-called Josephson constant, 2G J. And it was with excellent agreement. It was surprised because at first nobody knows where is superconductivity. When is the Josephson junction? And some people have idea that in one electron, alumina, because electron from alumina, interact with such amorphous carbon, and in second side also interact. And here is made so-called as junction. But it was era before CERN term and another tools for performing measurement. It was amazing because some phenomena were discovered, but up to present, nobody knows what is a source of such behavior. There are many critical article, many article in which people start to justify that it was indeed superconductivity. But I spent 3 years perform on the measurements and not have any publication from such, because in such time no such idea like now, but when you're performing some job and your PhD student, first is a PhD student, next place is people from laboratory, last supervisor. In such was situation where all people working in professor team, but documents said it is an interesting idea because I would like to tell you that sometimes people to discover some phenomena should work without good solution. Because I spent a few years and doing nothing from formal point of view. Because any publication now and when complete university and one start to be a postdoc, start work study in Poland and accept to be PhD student, I was a young soldier. Yes. It is a situation, but from time to time such conductivity back to life. It is interesting phenomena, and still people reporting new achievements such phenomena also inspiring many groups to introduce new method of investigation, new method of synthesis materials, and I show you how we can do it. Yes. In 1986 was discovered by Bertels and Miller superconductivity in ceramic. It was a surprise, like in carbon, because people believe that it only in metal and metal alloys can be responsible for such. With discovery such phenomena is also many job. It is also interesting for you, maybe, because they not intend to looking for or investigate superconductivity. They were a person from Institute Research and Development and working on ceramics. And it was ceramics, and it was important to such ceramics were utilizing for working as isolator for electric junction between metal furnace, for example, and electricity perform dielectric properties in low temperature. I don't believe in such story up to spend 1 month in synchrotron in Germany, because for performing measurements in low temperature, they need 8 liters of liquid nitrogen. But a bottle was, was 120 probably. As I remember, in Germany was 120, and they not able to fulfill bottle when it was not empty. And it was a Saturday. They left measurement, and when came to job in Monday, it was a job and start problem. Because I think that in all your institution, when you're working, it will be not any problem connected with preparing such glass ceramic or ceramic and perform measurement. And they publish article in journal which belong to his friend. He was editor-in-chief. To a friend, when somebody maybe publish it. It is also very nice story, but I don't know if it's true. But I maybe think that is true. Because many population of so-called physics decrease, because such so-called new superconductors contain in composition hazardous elements: mercury, thallium, lead, cadmium, etc. And most of physics was a focus of I will PhD work. I prepare. I know how to do it, and not have knowledge from chemistry that it is hazardous. And many people at conference, for example, it was about information conference booklet was in the frame because they were killed by hazardous elements because they preparing not have knowledge about it. It was like in USA, people looking for gold. Yes, and it is not because I find the gold. It's many situations. But how improving physics such idea? It was interesting because such materials, in such kind of materials, you can improve superconductivity properties. It is critical temperature and another materials when materials was not stocked. So when you have some deficit of oxygen, no full stoichiometry materials possess better properties, and it was one of element of such story and people activity which work. Not only perfect materials, maybe interesting, but also after some investigation, structure, and another, such materials possess layer structure and is depend of oxygen content, superconductivity at early or later. It was very interesting, but some methodology and chemistry which allow us a model with materials utilizing only simple chemistry method, it was amazing because in such time people improving their skills in preparing so-called layer structure. And here is, for example, opportunity to improve critical temperature when a particular layer are of nine superconductor were integrated but additional layers. And it was interesting that it was possible to improve many materials in such a way. It was so-called material engineering. It is the start era of material engineering when we able to intentionally modify structure. Because now we have better doing. They put some superconductor and bend in some different alcohols. Beer, vodka, wine, etc. And after immersing in such liquids, they perform measurement. In many times, they improve materials properties. It was connected with ventilation access coming from interlayer structure. What also? Some halogenide materials are very sensitive for non-stoichiometric structure. When we have ultra thin films, when we have some defect structure or substitution, we can improve significantly the materials properties. It is so-called materials at the edge. Yes. And also, we perform many experiments when we grow a single crystal for second harmonic generation, and after testing some crystals with some kind of defects, possess better opportunity to generating second harmonic. And also, it's possible investigate defected materials utilizing quantum chemistry calculation. It's a special conference focused on such topic. Defect materials investigated by two experiment and theoretical point of view. And here is my topic of our discussion with you, because it is not. I must deliver a talk for topic connected with course, but I have opportunity convey to you my experience and my work, my results of my maybe knowledge which I collected during 50 years. And now we can discuss about ultra thin film. You remember, because we discussed it, it is well known, like two voice discovery graph. What they doing? They utilizing pencil, sheet and scotch tape, and cover black card, put scotch tape, and go under transmission meters. And I thought that many my information, my meetings, my idea are in English. And I meet in Chennai, and we spent 1 week together at conference organized by Alma University with Professor Mohammed Hanin. It is an Arabic origin person, which is a director and famous expert of molecular biomechanics. And he employed Gelman and Novoselov, such Russian people which discovered graphene, and he rejected them from job when obtained a bill for maintenance of transmission process. And he told that it was one of the best decisions regarding human resource. And they moved to University of Manchester, and in summer, but in December they obtained Nobel Prize. As England citizen, because they obtained citizen morning before receiving Nobel Prize. Because politics is strange. Okay. But when scientists show what new opportunities give us two-dimension materials, it is not dots, it is nanoparticles, but a big sheet of materials, when we can model materials properly. It was amazing, but I first go to my topic. You probably don't know such experiment. When we put steel to heavy elements and ice, it is bluish ice, and it is passed across, because under pressure, melting temperature of ice is below zero. And ice melting below zero are under pressure. And for example, when you go to Himalaya and try to boiling eggs, you need more time, because the boiling temperature also is lower. And it was a fixed idea when stress or strain may be also influence of materials properties and effect. And it was also confirmed. I already show you a such a picture when we can able to improve a critical temperature of such perovskite utilizing stress, yes, when under pressure. But it will be interesting when we have opportunity to keep such materials in such pressure. What is done? When we have a special kind of method of thin film grow, we can use a so-called pseudomorphic growth. When your leg is bigger than shoes, sometimes it's possible. Yes, it is here is the same. We can we have a substrate, and atom by atom we building a new layer, and to a leader, it is a force. It is a Coulombic force which have a similar give a similar effect like pressure, because we can adopt when is a lattice of substrate is bigger when lattice constant of thin film. A thin film will be straight. When it's opposite there, it is like under pressure. And it was confirmed experimentally. I show you, we have many opportunities. Unfortunately, with, for example, with perovskites. Perovskites is always have some interest because we can adopt, especially constant, lattice constant of substrate to thin film, and we have opportunity to make stress or strain for thin film. And I see you that just moment that it is possible. It is looking like it. You have some opportunity to see example like it swap. It has a strained layer because lattice constant of substrate is bigger when thin film. And strain and stress also change many materials problem. I told you that we can make some materials which don't exist in nature. Because, for example, when we have materials under stress, when we release, it's back. Professor Tom, previous lecture. Sometimes when we not pass elastic property. And here is also strontium titanate. You remember about strontium titanate that it is over phase transition at 105 Kelvin. 105 Kelvin is minus 170 Celsius. It is not good for possible application. But next article with Nature, when people obtain a room temperature for electricity, strained thin films, which was grown on especially chosen substrate, which grow thin film. And it was a surprise when critical temperature, it was a room temperature. Maybe not in India, but in Poland it's above room temperature. Because in India, when I sometimes have a reviewer of some theses or some articles, room temperature is 303 in India. In Poland, 293, the same less. Okay, but as such experiment, such publication start a very fast growth of methodology, because it was more than taxi, and skills of experimenter to make so-called heterostructure. And we can make materials, building materials atom by atom in a situation that it is not possible. And I show you a few experiments which confirm it. For example, what is an interesting phenomenon? When I not make my PhD thesis from high temperature superconductivity, I ask director of science institution, Institute of Low Temperature Research and Structural Research in Poland. Maybe I have opportunity investigate theoretically coexistence, magnetism and superconductivity. And you know what is it that ferroelectricity from theory which was valid in such time, it was not possible because it was electron was made a pair, it was a boson, but ferroelectric is quite a different order. But 20 more than 20 years after my graduation, after my PhD, was experimentally confirmed the coexistence of superconductivity and magnetism in two-dimensional structure. Because people grow thin film on specially chosen substrate, and it was some new phenomenon. Kia is also experiment when we discuss. When I present it 50 years ago, people went crazy. He write not for measurements when ferrum and selenium will and tellurium may be a superconductor, but original bulk temperature critical is 14 centigrade, but under pressure is 21. But when we try to perform measurements of thin film, it's also the same. And when we grow on a special kind of substrate, thin film, temperature, critical temperature is like we perform measurements under pressure. But what is the difference? We have material which have a phase possess superconductivity up to 21 Kelvin, except 14. We have materials which have a permanently changed property. And also, when we consider materials, for example, for solar cells, this also is the same engineering of thin films. Because you know that all materials which is used for solar cells are thin films, important thin films. And people sometimes utilizing stress and strain between particular films to achieve, for example, wanted bandwidth. We can do more, but it is very expensive because I think that most cheap equipment for molecular driven detection when we put atom by atoms, it is maybe $2-3 million. It's expensive, except you should have some additional equipment. And here is also one of example when people utilizing one kind of perovskite materials but grow on different substrate and possess different properties. And, for example, we can grow materials which have distillate properties. Yes, and in such technology, one parameter, strain stress, controls many parameters of materials and sometimes gives us a very useful tool for improving materials properties in detail, because when we can use as a substrate different and last, I told you also about because we discuss in lecture connected with investigation of materials for lifting, for solar cells, that is necessary to investigate quality and properties of ultra-thin films. And one of tools which is made use for such kind of measurements is spectroscopic ellipsometry. It is very simple technique because we incident beam reflected from surface and reflected beam is analyzed in taking account intensity and change of polarization. And we can determine from such spectra many useful parameters of thin films. One is quality of thin films, thickness of thin films, sometimes the electric function, we have, for example, index of reflection. We have many information regarding materials. But what is it also interesting? When we grow heterostructure, because solar cells is a multi-layer structure, we can, during one measurement, we can able detecting and evaluate properties of few thin films. And this laboratory measure, it is possible to perform some measurements in a laboratory equipment. It's not so expensive. It is simple working in air, and we put samples, perform some measurements. We have only limitation with spectral range, because it is working up to 4 electron volts. When we have more complicated equipment, which is embedded in a vacuum chamber, we can utilize spectral range up to 6, 7, maybe 8 electromoles which cover most background of most materials. I performed some measurements in equipment was conjugated with synchrotron in Germany. In a local community, we have several such kind facilities, very open for scientists from all world. You can put application for measurements on synchrotron. In Poland, we also have a synchrotron facility. You can will be granted 1-2 weeks stay for measurements. You will not pay for consumables, you will not pay for equipment, and sometimes you can obtain a cheap hotel for living because when you came on synchrotron you only sleep and work because you attend 24 hours per day. And we perform a huge number of measurements. It is a very complicated system because we need sophistical process of polarization of light, but such apparatus give us, for example, perform measurements of interval transition in spectral range not available in utilizing different methods. This a good equipment, unfortunately not working at the present. But this in each synchrotron is a many station. For example, for XPS, for XRD, when you will have a special, very complicated structure, and when you perform measurements, crystal structure measurements under pressure, you give some opportunities, and it is free. And when you have an idea or your supervisor that it will be interesting, its situation is as follows. You check a website of synchrotron, put application for CAL, and waiting for positive sound from them. And next, it's necessary to gain to synchrotron, perform measurements, and write a very good papers after. And we also perform many interesting measurements. I told you about such surface phase transition and another experiments. And it shows that such open mind on tools which located in special measurement center are interested for developing and opportunity science. And here we investigate such phenomena and explain observe results, and after we can do new application. Now we utilizing different station. Now we move from tool as ellipsometry. Now we turn on infrared measurements and electronic structure determined by so-called XPS method. This also interesting tool for evaluate structure and explain observed phenomena. It is also utilizing for different kind of materials. From my point of view, it will be interesting when you, for example, check what measurements were done by previous investigator on such station measurement station because it is give some remarks, some advices how in which way necessary to prepare proposal for measure. And I think it will be all for today. I'm sorry that we are staying a long time from early morning up to evening. But I hope it is a chance to obtain some information which may be useful for some of you. When after my course somebody applied some little bit of knowledge on his own science, of her science, I will be very happy. We see tomorrow, yes?
The tutorial will continue tomorrow, second one. Thank you. So be here sharply by 9 o'clock morning.
He's so innocent.